Sir, you may take as much as time you may need, sir. It's completely
Okay,
fine.
fine. That's very generous. Usually Friday evenings, people have other choices. That's why I ask you. So this, I thank the Secretary of SNAS, Mr. Navneet, and the committee, student committee, and all of you students, as well as the faculty of Ship Technology Department, Cochin University of Science and Technology, my alma mater, for allowing me to speak about autonomous underwater vehicles. This is a very prestigious moment for me. Uh, so I'll just, yeah, the slide has changed for you. I've moved to the second slide. Are
Yes,
you?
sir.
Fine. So just checking whether the slides are moving. So this is the contents basically. So I've divided the lecture into 4 sections. The first section is the longest section. It will take almost an hour. It is on AUV design and development. So the first chapter in this section will be an introduction to AUVs. The second chapter will I'll speak about the configuration of AUVs, and the third chapter will be about the dynamic mathematical model of an AUV. And chapter 4 will be about AUV simulators. Then we'll briefly discuss about the challenges that an AUV developer or somebody who uses an AUV face, and emerging trends in this particular area of domain. And this section 4 is on your request, research on job opportunities in this particular domain, which Navani requested me to add. So this is all about it. So I think the first section will take about an hour, and the next 3 sections, most likely it will be over in about 10 to 15 minutes. So the last 15 minutes, I'll leave it open to the floor for questions or any interaction. Fine. So this is the first section, design and development of AEVs. And the first chapter, let us begin. Introduction to AEVs. So what are AEVs? I'm unable to see the screen. Yeah. Yeah. So unmanned underwater vehicles. So what are unmanned underwater vehicles? So unmanned underwater vehicles are a class of submersible vehicles, which obviously, as its name suggests, work underwater. And these uh, contain independent propulsion systems and are capable of carrying payload sensors such as sonars and oceanographic measuring devices. So these are what are called unmanned underwater vehicles. So this, why are they required? First of all, see, marine environment is very challenging, and whenever you want to do some task underwater, particularly in the open ocean or in the coastal region at the harbor, these are very dangerous and challenging environments. So this unmanned underwater vehicles are highly desirable as force multipliers, as they limit the level of human involvement in high risk missions. So this is a broad classification of unmanned underwater vehicles. We have autonomous underwater vehicle. They are completely autonomous. You can see this first picture is of an autonomous underwater vehicle. This is completely detached from the user, except through wireless communication. You pre-program the AEV and deploy it. It does the task and it returns back to the user, and it is recovered. The second class is ROV. We call it remotely operated vehicles. So this you might have seen. I believe all of you must have seen the movie Titanic. So in the beginning, you see some robotic equipment which goes down and captures videos of the shipwreck. So that is basically a tethered vehicle. It is called a remotely operated vehicle, and that is being piloted by an operator who is sitting on board the mothership, and he's seeing the data also in real time. So this is basically used extensively in oil and gas industry for inspection of underwater assets such as pipelines, offshore structures, etc. Uh, so this is not fully autonomous. It is in fact a semi-autonomous or you can say call it as an automated system, or not even an automated system. It is in fact controlled by remotely, and in fact there is an option in which it can have its own battery system and propel. But generally, what happens is that the power is also supplied from the mother platform through an umbilical. So the tether that you see here, it is a hybrid cable which can give power as well as communication to the base station as well as to the ROV. And then there is a class of vehicles called gliders. So gliders are nothing but they are intelligent, little more intelligent propulsion systems. Perhaps the person who invented the gliders are maybe the person or persons may be more intelligent because it is energy efficient and it consumes much lesser energy compared to the other systems, in which that it does not have a dedicated propulsion system. Of course, the modern gliders are coming with a propulsion system to assist in increasing the speed or in emergency cases. But otherwise, the glider uses something called a buoyancy system, a variable buoyancy mechanism, and it uses this variable buoyancy to propel itself. Okay, so for example, in the case of an AUV, they use thrusters or propellers to move ahead, and then there are rudders or other thrusters to change the direction of the motion. The same applies to the ROV as well. So when it comes to gliders, so all these thrusters are consuming battery power, right? So gliders, what they do, it will be initially negatively buoyant. So when you deploy it in water, somebody throws it into water, it sinks because of the weight. Weight is greater than buoyancy, it sinks. Now, when it reaches a preset depth, the depth sensor senses the depth, and then there are different types of mechanisms in which the buoyancy of the vehicle can be varied. It can be a bladder mechanism, or it can be a piston kind of mechanism, wherein the intact volume of the vehicle is varied, so that as the buoyancy increases, the glider starts ascending. It starts, rising to the surface, and as and when it reaches a predefined cutoff depth, again, the buoyancy mechanism is deactivated and it returns to its original state. So, wherein it keeps on oscillating between a depth column. So this kind of equipment is, in fact, it is a low-speed vehicle because it is moving primarily on the buoyancy of the vehicle. It's a low-speed vehicle. It is extensively used for oceanographic measurements, and that also sustained measurements for months. So this can be because it's a low-power system. It can be deployed for months altogether. Say up to 6 months. Also, there has been history where a glider has continuously operated. So this is being used extensively by oceanographic institutes to collect oceanographic data in a particular region. And very recently, navies also multiple navies around the world are using it for data collection, mainly oceanographic data, and mainly the salinity profile for improving their sonar systems. I'll touch upon the sonar part and all as we move along. Also, they are using it for some military applications as well. So, why does it then have a propeller? That is for emergency purposes. As I said earlier, the gliders are low speed vehicles. So, in case of an emergency, or you need to steer it away from certain regions, then you use it as an option for additional thrust. So this is the ROV. Already we have discussed. There is a mothership from which the ROV is deployed. There is an umbilical, and some ROVs have a tether management system or an intermediate management system which has some subsystems sitting inside, and then the ROV goes down. It can also have a manipulator arm, to slowly go close to a object of interest and inspect it. That is what you see in the movie Titanic. It slowly, goes very close to the shipwreck, and it gives you a very close feel of the what is happening underwater or in your area of object. Interest. Now here, again, ROVs are not a very dynamic vehicle. These are also slow-moving vehicle, and these have multiple thrusters to control it in the vertical and horizontal planes. That is how it is positioned. And the power is almost always given by the mothership for sustained operation for longer durations, and it is passed on through this umbilical. And then the communication between the base station where the operator is sitting and the ROV, communication from the operator, like the commands to the ROV. It will be the modern ROV systems are very easy to operate using like joysticks or even to operate the manipulator arms also, there are some manipulator kind of, I forgot the name, what they call. They just wear it and, operate the manipulator to pick up, even to pick up objects. The sensors that typically are used are, for example, underwater cameras, because it is able to go very close to an object. You can use an underwater camera to closely see the object of interest, and also maybe sonar systems. So all this live feed will be received by the operator in almost real time. That is the advantage of an ROV. So this is very effective for inspecting periodic health of underwater structures or undertaking some repairs, etc. Let us move to the next slide. This is Glideup. So already we discussed this. So this is a sawtooth pattern that this trajectory is called a sawtooth pattern. The glider dives down on its own weight, and then because of the buoyancy, it comes up, and then it keeps oscillating in the water column. And periodically it surfaces, and it has a wireless communication system. Most of the time, it can be satellite communication, so that it is you just deploy it and come back to your office on land, and you just relax and sit here. You'll get all the data periodically, and this can go on until there will be an auxiliary battery on board, which is powering the sensors which it is carrying. So until that life, or until the mission period is over, this can continuously do the surveillance. So what are its uses? We already discussed them. So I'm not going into details because this is all more about AUVs. So coming to AUVs, AUVs are more autonomous compared to the other two classes that we saw. And these are a class of unmanned underwater vehicles that are pre-programmed. Okay. So again, pre-programmed is a necessity, and it is deployed from a base station. So it can be a mothership, and modern AUVs can even be programmed at land, and then you just deploy it at harbor. So this is also possible nowadays. And it goes into the sea, executes the mission, and it periodically reports to base, that is through its communication system. And after the mission is completed, is recovered post-mission. I think some people are waiting to join the room. Just have to keep that. Yeah. So, and once the mission is completed, they are recovered, and the data is analyzed. So this is the photographs that you see here are basically the steps in the an AUV mission, the phases in an AUV mission. The first section, the first phase of the mission is to plan the mission. So this often happens at the base station, and human is involved in this. So you have even smaller AUVs are done even on tabs. Mission planning is done on tabs. For more sophisticated and bigger systems, you have a dedicated control station. So there will be a map which can be either an ENC chart or a suitable bathymetric chart. And you can plan the mission using waypoints, and then you also preset all the sensors on the AUV. Okay, basically the aim of the AUV is not just to go and come back, isn't it? It has certain sensors. It has to execute as per the mission requirement, record and retrieve the useful data, or do some surveillance and reporting, etc., and come back. So then once the mission plan is uploaded to the AUV, this often happens through either through a umbilical cable, which is connected to the AUV and then removed before it is deployed, or wireless through Wi-Fi or whatever. And then it is deployed into the sea. The second phase is launching the AUV, and then it dives underwater and undertakes mission. Okay, so commercial AUVs operate at very high depths. Whereas in certain other applications like military applications and all, the depth is restricted due to the strategic nature of the mission. So this other photograph shows a AUV going close to the seabed and imaging using a light, LED light, basically for the camera to record what is underwater. Or you can see here that the sonar is it is depicted that the sonar is imaging some object that is underwater. And see, this is a typical image, a side scan sonar image. What the AUV images, scans while it is scanning the sea bottom. So this data periodically, again, once the AUV surfaces, whatever important data is there, it can be communicated to base. I'll touch upon all these details in subsequent slides, and also including the summary of the mission, the position of the vehicle, and the health summary to the base. Now, once the mission is completed, it is recovered and then cleaned. So these are the other things that happen: data download, health checks, battery recharging, and redeployment. Redeployment if necessary. Otherwise, it is taken home and you come back home, have a nice meal and sleep. If the mission has to be continued or some part of the mission is remaining, you again redeploy the vehicle. So these are the various AUV applications. So we discuss about why AUV is required, basically for convenience of the human and for the safety of the human. Okay, because marine environment is very challenging. For improved efficiency, improved safety, sustained missions, which humans cannot do, we use autonomous underwater vehicles. So the first and foremost application is oceanographic data. It is a bathymetric survey. So this has been going on from much long ago. Even the oil and gas industry, but particularly in European countries, and under ice exploration, the internet cables and pipelines are all passing under the ice. So the inspection of these cables and all these things, AUVs have been used extensively. And Canadian AUVs like IAC Explorer, these have been used for even cable laying. So and this is another application. Rapid environmental assessment. If some say some event happens, it can be a natural event or an artificial event, human-made event like an oil spill. So to rapidly assess the environment, you can deploy an autonomous system, and then it can report what are the changes happening. Okay. From the last couple of decades, military, okay, of course, the autonomous underwater vehicle development started with the military as any sophisticated system. But navies around the world have started utilizing AUVs in their warfare, surveillance. A very common application in which AUVs are very successfully used are mine countermeasure missions, in which, like the land mines in times of war, the most common and cheapest source of weapon that is available to the enemy is mines. So they lay mine in clusters in areas of transit, maybe near your harbor or in transit lanes that you are likely to go. So it can be severely damaging to your fleet. So then there are various mechanisms to identify and clear the mines. So autonomous underwater vehicles are one among the various tools or various systems like minesweeper ships, and several other systems which are utilized for identifying that a mine has been laid or a cluster of mines have been laid, and then reporting to base that okay, this has to be neutralized. And then even certain autonomous systems are used for neutralizing the mines. Okay? And then ASW is anti-submarine warfare. So it is very difficult to detect a submarine. The main asset of a submarine is stealth. So to detect and track adversaries' submarines, we commonly use autonomous under. In fact, this is a we can say in the last decade this has come up as a potential game changer because of the increase in submarine fleets of adversaries. Multiple navies around the world are utilizing autonomous underwater vehicles as a cost-effective means for sustained surveillance in order to detect submarines. And then it will be reporting to the base station that an adversary submarine is there in my area of interest or in our own waters. You take necessary action. As of now, like aerial drones, that weapon launching capability has not been inculcated into autonomous underwater vehicles, but that is not very far away. Then, asset protection. Your own harbor or your own coastal defense systems, you want to protect from enemy incursions. you want to protect against a swimmer who is coming and delivering an explosive and going away. So this autonomous underwater vehicles can be used for sustained surveillance and patrolling. Choke points like the South China Sea, we have several choke points wherein the adversary is coming through a channel and entering your own waters for whatever attack or surveillance. So these choke points can be effectively surveyed by or guarded by autonomous systems. So this is another potential application for autonomous underwater vehicles. For example, the Malacca Strait. And there are several maritime transit lanes. So around islands, So these places are where are called choke points. And when a fleet of submarines, say for example, exits a harbor, there can be some transit lanes and channels and all. So these are kind of choke points where you can. The biggest advantage of an autonomous underwater vehicle is that its signatures are very less. It is smaller in size compared to conventional platforms. Noise levels are claimed to be lesser compared to conventional submarines. So it will be difficult to detect it. So it can hide somewhere and record and your signatures and report to the base station, or the adversary signatures and report to base station. And of course, for search and rescue operations, when aircrafts crash or when you lose a particular object of interest in sea, you can utilize autonomous underwater vehicles for carrying out search and it is part of search and rescue operations. But AUVs generally don't rescue anyone. It just reports that okay, somebody is found here. And any maritime intensive activity, AUVs, I would like to call them as a force multiplier. So often people tend to see AUVs as the only soldier who can execute same MCM operation or ASW operation. No, it will be used as a force multiplier. It will be only one agent among multiple agents to carry out any strategic or maritime intensive activity. And another interesting aspect about an autonomous underwater vehicle, it is not a generic design. Unlike a cargo ship or a general cargo ship or a bulk carrier, which all these class of ships will be alike. But in the case of AUVs, there are multiple types of AUVs which are very difficult to classify based on application because they are role centric. Okay, each AUV, a developer will be designing and developing based on a particular user requirement. Okay. So, and these requirements, say for example, Indian Navy will want a particular type of Navy for ASW operation. Now, ONGC will want a particular type of AUV for its pipeline inspection. So these applications will be contradictory, partly contradictory, not completely, partly contradictory. So this nature, and these are specific in nature. That is another aspect of it. So it calls for a large variety of vehicle configurations. So for example, with regard to the speed, when you're operating a particular sensor, for example, an imaging sonar like side scan sonar or a synthetic aperture sonar, you need to operate at a particular range of speed, like say 3 to 4 knots. If you operate at higher speeds, you will not get proper images. And then depth requirements will be changing. The endurance requirements will be changing. The range of how much distance it has to cover during its mission or during the transit. This varies. Launch and recovery, whether it has to be deployed from a ship or it has to sail out from the harbor or it has to be deployed from a boat, whether it has to be man-portable or slightly bigger system. What are the payloads required? What are the communication systems that can accommodate? So based on this, these are role-centric designs. So for example, the first picture that you see here is the system that we are developing. It is an indigenous system called the High Endurance Autonomous Underwater Vehicle. So this had come in the news almost 6 months back. So DRDO is developing this vehicle system with NSTL as the nodal lab and multiple other DRDO labs, including a major lab from Kochi called NPOL. Okay, and several other labs. I'll touch upon this when I come to that specific slide. And Cochin Shipyard Limited is our industrial partner in integration and development of certain subsystems. So this particular trial was done at Kochi. We are right now in the development phase. So this AUV you can see here, it is almost like a cigar. It is a torpedo kind of shaped AUV, completely cylindrical. Because of which mission requirements, and it is completely pressure rated system, except for the nose and few sections which is flooded. Most of the sections of the vehicle are flooded. Now we come to the second picture. It's a flat. This is called a flatfish configuration. In fact, DRDO also had developed a flatfish AUV. This is a commercially successful AUV called Saab. Double Eagle from a company called Saab. Now this is means it is configured in such a way. It's a double hull configuration, wherein you have the pressure hull inside and an exhaust structure and two pressure hulls, or even you can have multiple cylindrical shells also. So this needs to stand at a particular depth, which we call as hovering. Hovering means you need to stand at zero speed, zero forward speed, but you need to maintain the depth. Okay. Most of these autonomous and all of these autonomous underwater systems are positively buoyant, meaning which it will float on the, suppose the propulsion is switched off or at equilibrium, this vehicle will float on the sea surface. Okay, this is primarily for the safety of the vehicle and ease of handling of the vehicle. So what happens dynamically, if it wants to stay at a particular depth, there has to be some control force. So this is given either using rudders or in the case of plus firm configuration, the stern planes, which are the horizontal rudders. In the case of an XCOM, all four rudders will be acting. Or we can even use thrusters. So this particular AUV uses vertical tunnel thrusters in order to stay at a particular depth. It stays at a particular depth and deploys other smaller autonomous systems for executing the task that I said earlier, like mine neutralization. Okay, this is one application. This looks completely different. The configuration itself is completely different from the first picture. Now, the third picture is another Russian AUV called Glideup or Harpy shot. So this is again looks very similar to a submarine. So this is the first picture that you see here is completely axisymmetric, whereas this is more like a submarine where it has an asymmetry here, and it has an open structure. There is an exhaust structure, and all the internal electronic systems are in individual modules. So this, based on configuration, if you classify AUVs, it is broadly like axisymmetric configurations are more common. Torpedo-like forms are more common because they're easy to manufacture, handle, and also model. The plan, the mathematical modeling becomes very easy. And it is also hydrodynamically more efficient compared to a flatfish form. And there are non-axisymmetric hull forms like a flatfish form. There are single pressure rated outer hull like the first picture, and an exhaust structure with individual pressure rated modules with it. So these are the various types of AUVs based on configuration. Now, based on the weight class, there are again you can classify it from very small micro AUVs like this. It's also a biomimetic AUV, which means it is designed to behave like a fish. It does not have a conventional propulsion system. It has a flapping tail. It flaps like this. Video is available in YouTube. You can see that it is from MIT. This robot is called Sophie. So it's a biomimetic AUV where it is mimicking fish, but they're very slow moving vehicles. Even IIT Kharagpur, IIT Madras, and IIC Bangalore are collaborating and developing a biomimetic AUV. It's a first of its kind major development in the country, a small fish-like AUV. Then there are man-portable AUVs. So you can see here a single person deploying a vehicle called, this is like ECA-9. It's a very popular AUV in the global market. So he's just standing on a small platform and just gently putting it into sea, and remotely it will be switched on. So this is say 15 to 50 kg plus. Okay, the first micro AUVs are less than 15 kgs. Man-portable AUVs are extensively used for mine countermeasures and oceanographic purposes. And then comes lightweight AUVs. So they are between 50 to 300 kg class. So this requires some kind of a mechanism. It is not a heavy mechanism, but some kind of a lifting mechanism for deployment as well as recovery. Man-portable AUVs can be picked up by a single or two people even. Heavyweight AUVs are from the range of 500 kgs to 2000 kgs, so 0.5 to 2 tons class. So this requires again, It has to be launched and recovered using heavy duty cranes. Then comes last displacement AUVs. So it is meant for high endurance. So this can okay. The endurance of say man portable AUVs are typically between 3 to 4 hours. Micro AUVs are even lesser. It can hardly last maybe half an hour or so if it is having conventional battery system. Lightweight again it depends on the locomotion. The slower or if you have an efficient locomotion, it can sustain for longer period because you are drawing lesser current. Now, lightweight AUVs and heavyweight AUVs typically again 4 to 6 hours, maximum 12 hours. So this is the typical range of even 24 hours. There are some AUVs in the heavyweight class like Eugene and all, which gives the endurance. Now, when it comes to high endurance, you are talking about days. So you deploy the AUV for say 15 days to 30 days. So this is the type of endurance that you are looking at. So this AUVs fall in the range of 2 to 10 ton class. Okay. And this requires again sophisticated mechanisms for deployment as well as recovery. And then there are XLUVs called extra large unmanned underwater vehicles. These are almost like mini submarines, but they're uncrewed. There are no crew involved. This can vary up to 20 tons to even 50 tons. So this is one of the very popular. Not. Of course, it is used by the U.S. Navy. It's called Orca. It's from Boeing. So you can see here it is being inaugurated by a lady, must be a lady of some senior naval officer. So she's breaking a champagne bottle, very similar to our case where we break the coconut. Here she's breaking a champagne bottle. So this Orca, if you can just imagine the size, it is it is almost I think 20 meters or so. I don't remember the exact dimensions right now, but it falls into this class, almost 50 tons, and then it can stay underwater up to 6 months because it has a diesel generator and a snorkel. So periodically it comes, to surface and charges its batteries and then dives down again. So this is these systems are used for again, strategic applications like supported by navy's requirements around the world. So there are several other uh, extra large unmanned vehicles which are popular around the world among few navies. Indian Navy is also, uh, calling expression of interest for developing such systems indigenously. So these are some popular AVs which have been, which are part of the autonomous underwater legend. So in 2003, the US used Remus 600 AV class of AV. Remus is from Hui, Woods Hole Oceanographic Institute, so Massachusetts. So these AVs were extensively used in Iraq War. The 600 denotes that maximum depth rating is 600 meters. Okay. So, and this was used for mine countermeasure operations to detect mines, and it detected mines successfully. This was a major achievement. You must imagine 2003. So, using the side scan sonar, it detected mines, and I think it was deployed in a harbor close to Iraq only for the US forces to infiltrate. And then Rema 6000 was used for the crashed aircrafts AF 447 in 2011, and it successfully detected the black box pinger. So this is how the Remus gained immense popularity. 6000 again means it is rated for very high depths, 1000 meters. Then comes General Dynamics Bluefin. So Bluefin series of AUVs are also extensively popular. These are very successful and reliable equipments. It was used in the crash of Malaysian Airlines MH370. Of course, as you all know, it could not detect, or in fact, this is only one of the agents who are searching. There are multiple ships, submarines, everybody is searching, and AUVs are deployed by somebody, as a cost-effective means of surveying certain areas. For example, the seventh arc in the Indian Ocean, just very close to Western Australia, this area was covered by this AUV using side scan sonar. This underwater topography or the underwater seabed was completely mapped by the AUV. And this was the first time this particular region was surveyed. Okay, and even continuous 27 hours it was deployed. How they do it is that they deploy multiple numbers, and they keep AVs as standby. And if it is quite often it is what happens is that some of the systems develop issues. Okay, because marine environment is very challenging, and then you recover it, and you deploy a alternate AUV. This is typically what they do. So it was used over 21 operational days. It is enormous performance. And the Huygens AUVs, this is from Norway, from a company called Kongsberg. So Huygens series of AUVs are extensively used by a wide variety of customers around the world for hydrographic survey, whatnot, MCM, military applications, etc., etc. The ISC Explorer series again, beautiful AUVs. This is where I think your professor Manoj Isaac sir has worked for a brief period of time in Memorial University, Canada, right, sir? So they have a series of AUVs, TCU's Explorer, and there is a bigger AUV. I'm forgetting the name. So these were used for multiple purposes. I think the bigger version of this was used for cable laying and all under ice exploration because they are very close to the Arctic. Okay. This is also another Canadian AUV called Solas from Cellular Robotics. So this AUV is also very popular. It is used for multiple applications, including submarine detection. And this one version of it even comes with the fuel cell. So fuel cell is, as all of you know, it is based on air independent propulsion, where it can give you sustained endurance compared to batteries. Of course, this can be used only in larger AUVs. And there is a concept called suction anchor in this particular AUV, wherein the AUV is able to switch off its propulsion and then anchor it to the seabed and stay there for a long period of time. So this gives an advantage to the system that it is able to stay dormant and become active only when it is required or triggered. And another aspect is that the sonar systems, particularly passive sonars, when the vehicle is moving, it is affected by flow noise. So the flow disturbance creates some noise and also the self noise of the AEV because the motor is running. There may be actuation systems. So all these motors will create self noise. This noise will deter the sonar from detecting outside noise. So sonars detect external noise from other platforms like ships in order to detect them. So if you are staying silent and not moving, then it improves the range performance of the sonar. Okay, Sophie, we are already introduced to Sophie. Fine. So these are the AEVs in India. NAO Goa, they developed Maya. This was probably the first successful AEV program in collaboration with Portugal, University of Porto. And recently they have developed another AEV called Coral Boat. So these are mainly for oceanographic purposes. NSTL had developed Blackfish AEV. It was a technology demonstrator project wherein the AV systems were first introduced to NSTL. NSTL, as all of you, we have visited NSTL. So NSTL is mainly a weapons lab, torpedo systems and mines for Indian Navy. So Dr. Manu Kurula and Dr. Bhargava Srinivasan Iyengar, they were alumnus of NSTL. Sorry, Cochin University, our ship technology department. They were key people in developing the Blackfish AV and introduced AV to NSTL. Put NSTL on India's map of AVs, and then several AV technologies were developed. And right now we have two active AV programs. One is the high endurance autonomous underwater vehicle, and then we have a man portable class of AVs which work in a swarm configuration. This is a very interesting project. I'll touch upon this subsequently. So these are two AV programs that are running here in collaboration with other DRDO labs. And also our industrial partner for the HEAV program is Cochin Shipyard. AUV Swarm they are working with Bharat Dynamics Limited. And of course, several other industries. There are several MSMEs, and if you take the map of India, we can populate the entire country is working on these two programs. And CMER at Durgapur, they had developed two systems called AUV 150 and AUV 500. I believe, again, 150 and 500 denotes the depth ratings. NAOT is National Institute of Technology, Ocean Technology in Chennai. It is, you may be familiar with it because they are developing the first manned submersible program for the country, Malsia. And they have developed several ROV systems because they do underwater exploration for identifying minerals and other underwater assets. Okay. L&T has developed two AV systems called Amog and Adamya in collaboration with international agencies. GRC with Salem Aerospace is a private company. So they, in collaboration with Salem Aerospace, recently developed a man-portable class AV called Nirakshi. ECIL has developed Electronics Corporation of India Limited, ECAAV 500. Bharat Forge with Artisys, they developed an AV called MRAV. And several startup firms are, left and right. Okay, what I'm trying to say is that in India, this AV field is booming. So what happens 10 years back with the unmanned aerial vehicles is now happening with the autonomous underwater vehicles. So several startup firms like IRO, Plansis Technologies, I4 Marine, Sagar Defense is a private company. So these are all firms are aggressively into AV and autonomous systems manufacturing development in the country. Among academia, IIT Bombay has developed student AUVs and their IIT Madras, Delhi Technical University, IIT Kharagpur, SRM, and many more colleges. And the main intention is to participate. Students come together under some faculty and develop AUVs, and they participate in AUV competitions internationally. And many of them have won accolades in international competitions, very prestigious awards. Okay. Indian Navy is the largest operator of autonomous systems in India. They are the single largest user. So they are using at least two varieties of Fusion AUVs. I think NIOT is also using a Fusion Superior. And they're using an AUV called AUV 6280 from SAP, which is for mine countermeasures. No, sorry, it is for acoustic target. So it is to simulate, mimic a submarine. When you practice your weapons, you cannot risk your own submarine, right? So they put targets that mimic a submarine, which creates the noise of a submarine. So the weapons will actually be fired, and it will try to home on to this particular AV. And then ROVs are used. And SAP Caster is another small AV which is for mine utilization. Various other agencies are also using AVs like NIOT, ONGC, hydrographic departments, shipyards, etc. The second chapter is about the configuration of AVs. Okay, so let us start with the product breakdown structure. Autonomous underwater vehicle. So what does that system contain? Basically, there are vehicle subsystems. Okay, and there are C3 systems. C3 systems matlab command, communication, and control. Okay, and support system. So coming to vehicle systems, there are various technologies and subcomponents involved, like hydrodynamics of the vehicle and controls. Hydrodynamics is one area where naval architects are working on, and control systems. Okay? The control plant of the vehicle, navigation and guidance, embedded systems and instrumentation. This is where our friends from electronics background and computer science will be extensively working. Of course, instrumentation background as well. Electrical systems, battery. Most of the AVs work on battery systems. Okay? And as all of us know, all these electrical systems are nowadays working on lithium-ion batteries because they are the most efficient. And in that given form factor, all AV systems and sensors are specifically developed because these are smaller vehicles. No, so you need compact sensors, and they need to be efficient in that form factor. So lithium-ion batteries give a great advantage with respect to form and weight. The mechanical systems, because as we have seen, these AVs work at higher depths, right? Ranging from 100 meters to 300 meters to even 1,000, 6,000 meters. So as you know, the pressure increases tremendously as you dive underwater, and the mechanical systems play a key role in protecting the internal subsystems from getting crushed. All of us have seen what has happened to Titan, the manned submersible which collapsed, isn't it? So that's a very tragic incident. So I have not come across any AV which is crushed that way, because most of the systems are mechanical systems are very nicely designed and meticulously developed. Data security, of course, this is a very relevant field today. The data that you store, if it goes into enemy hands, like often what happens, autonomous systems are picked up by enemy adversary navies, then that data will be encrypted and stored so that it will be difficult for him to access the data. And in some cases, what happens if you enter the key or the SOP of accessing the data is violated a number of times, the stored data will be erased. So that is another advanced security feature of security. And another thing is communication. While you're communicating the data, enemy can intercept. They can be at a standard distance and they can intercept. So during this time also data will be encrypted. Payloads. This is, most of the AV payloads include sonar systems, oceanographic sensors, navigation sensors, etc., etc. Then recovery aids. Recovery aids, matlab, you are sending this chap alone into the ocean. Now, at the time of recovery, certain subsystems will help the recovery team to identify or see the AUV and recover it. So one is visual aids, like there will be lights flashing on the AUV. The other one is a beacon, okay? Communication beacon, which continuously sends the current position of the AUV. Other things can be if the AUV is unable to surface, say it has sunk, then there will be pingers, okay, or acoustic modems which give distress signals. So the recovery teams goes searching with the hydrophone and it picks up the AUV coordinates either using a USBL system, which is called an ultra short baseline, or a normal sonar can pick up the pings and try to locate the AUV and recover it. So these are some of the recovery. Now coming to the command, control, and communication. What is very crucial is the mission control station. Okay? This often is on land or on a mothership mode. So wherein the operator plans the mission and the mission is evaluated before transferring it to the AV using a simulator or some other means, and then it is transferred to the AV. And while the mission is going on, the AV keeps on communicating with the base station. Okay? It can be through acoustic communication, which is underwater, or through surface communication. We'll compare both in some of the subsequent slides. And then in certain cases, what happens midway through the mission, you may have to replan the mission. See, the operator sitting at the base sees that some scenario has changed or the AUV is not performing as intended. Then he replans the mission and communicates to the AUV midway the mission. So this is like mid-course correction. And yeah, simulator already discussed. Now support systems, particularly the larger AUVs require dedicated launch and recovery systems and handling mechanisms for safely transporting the AUV, storing the AUV, moving the AUV around, because it is as you can see here, this is again a layout of ISE Explorer. There are multiple sensors around, including sonar systems, wherein certain transducers and all, if there is some kind of pressure applied due to mishandling, they'll be damaged. And then you'll be talking about repair or losses in terms of crores. So this has to be handled very carefully. Yeah, and other support systems for vehicle systems. So this all come in terms of support systems. So what are the key technologies? The key technology, what I would list is basically the navigation systems. Okay? Navigation systems include localization using an inertial navigation system, aided by a Doppler velocity log and a GPS. This also I'll show it to you in a subsequent slide. So I'll just quickly go through here. The motion planning and obstacle avoidance. The operator plans the mission using some waypoints, which are lat-long based. It just gives you, say, for example, 10 series of waypoints. The AV has to go sequentially from waypoint A to 1 to 10. So then the navigation system identifies its own location and passes it on to the onboard computer, which does the motion planning, considering the sixth-off motion of the vehicle, the dynamic motion of the vehicle capabilities, and while moving, any dynamic obstacle or static obstacle which is unplanned, the sonars detect and the AUV has to maneuver in order to avoid the obstacle. Then there are some mission payloads like imaging sonars, or so this image or whatever data is collected, that processing part and automatic detection of targets. Okay, this is a very common feature that the user expects the present AUVs to have. Then power management and distribution. So this AUVs will be having a plethora, a number of sensors which are operating at various voltages and currents. So then from the main battery, we'll be mostly working on a particular voltage and current depending upon the nominal requirement. So from there, you will tap and distribute all these other payload systems. So you need an intelligent power management and distribution system. So this is another critical system. Yeah, sonars we already discussed. Front-looking sonar, side-scan sonar, and synthetic aperture sonars. Let us not discuss much about these things. Communication and tracking. Yeah, this is another important, very critical thing. Once you deploy the AUV, it is like the child has gone away from the mother's hands. Okay. So unless it comes back, at least the developer or the operator will be under immense pressure. You don't know what is happening because it's a very uncertain and dynamic environment. When you are deploying the AUV, it may be C state 2. Okay, but maybe afternoon or in the course of a day, the sea state changes. In fact, in the course of few hours, the sea state changes, and then it becomes sea state 4 during recovery. There is every chance that you will have a very tough time getting your AV back safely. So what I was trying to say is that you have to depend on wireless means of communication. So one is acoustic communication. Acoustic communication ranges are limited because of the physics. Underwater, the ranges are very much limited. You can get with the present technology, you can get around 2 to 3 kilometers. That also the baud rate will be 500 bits per second to 1000. Sorry, 1 kbps. Yeah, 500 bits per second to 1000 bits per second. So these are the kind of baud rates and ranges that we are talking about. So when you talk about long range operations, acoustic communication is not going to help you in order to track or communicate with your AV. So then you have to use surface communication system, wherein the vehicle has to come to the sea surface and use either line of sight like UHF or other means of communication. Again, those ranges are limited because this antenna heights are very less from the water surface. Okay, so you get like 8-10 kilometers sort of ranges with the line of sight communication. And then you have to depend upon satellite communication. For beyond that, you have to depend upon satellite communication. So wherever the satellite is having coverage, you get that. This communication, again, satellite communication bandwidths are very limited, particularly Indian satellites. So this becomes a very critical factor. And this is, in fact, limiting the autonomous capabilities, I would say, because of data transfer limitations. The moment you get a high-speed communication system, the complete scenario is going to change. Particularly in case of operative navigation. The future is definitely multiple autonomous underwater vehicles working together. So their communication is going to play a very crucial role. Health monitoring and fault tolerance. Okay. So there are multiple electronics subsystems, electrical systems, mechanical systems working in tandem. There is a very good chance that one or many of these sensors develop faults during the operation. So you must take precautions so that this does not lead to a cascading effect. The one failure leads to another failure, or finally the vehicle is lost. So this health monitoring has to be done by the onboard computer in the vehicle. And then some fault is happening. It has to isolate the fault. It has to protect it has to see whether it can isolate the fault. If possible, yes. Otherwise, it has to take precautionary measures like compromising the mission and for the safety of the vehicle, and indicate to the base station that I have some problem, please attend. Okay? Of course, swarming or cooperative control is a very relevant topic today, and people are working on it. It is a work in progress everywhere. This is going to be the future, wherein multiple AUVs work together in a cooperative and collaborative approach. Okay, I didn't know where to put these slides, but I think this is appropriate place. Basically, we talked about the hardware part of the vehicle architecture. Now coming to the software architecture, there are various software architectures. Software architecture is perhaps the heart of the AUV. Of course, the embedded system hardware also comes into the picture there, the kind of hardware that you choose. But most of the hardware systems are available off the shelf right now. Now, this particular software framework, is a very popular framework which is made by University of Porto. LSTS is the department which has made this. So it is called the mission planner, the supervisory of the high level planner at the operator level is called Neptus, and the architecture on the AUV, the software architecture on the AUV is called Dune. These are open source softwares. So left and right, everybody in the world is mostly either using this particular framework, or there is this is called Dune and Neptus from LSTS, University of Porto. Or there is another framework called Moose, which is developed by MIT, I think. So that is another architecture which people use. So as you see here, the Neptus does the mission planning and the commands are given to the plant supervisor. Okay. So it gives the command to the vehicle supervisor, which can be the main computer. And then the main computer evaluates this incoming command, generates the necessary maneuvering command for to the control plant. Okay. Here they have given an example of a PID controller, which is 99% of the time PID controller is used for most of the AUVs, and wherein it actuates the thrusters and fins for maneuvering the AUV. Okay, thrusters mainly for the forward motion, and fins are for controlling, maneuvering the AUV in vertical as well as horizontal plane. And then feedback comes, okay? And the feedback goes to the plant. And then there are navigation sensors. Navigation sensors are used for localizing. Localizing, in simple language, to know where I am. In fact, the command is to go to XY lat long. Okay, but I have maybe I am traveling to XY. I have reached X dash Y dash, and my attitude instead of roll being 0, that 60 degrees of freedom, roll pitch and yaw. I am maintaining an attitude of roll say 5 degrees. So this is what the navigation sensor gives. So this is a localization, means your own position as well as your attitude. So this information is given by the navigation sensors, and the states are given to as an input to the onboard computer. And then there are navigation sensors working on collision avoidance. So this is a simple architecture which has been successfully used on most of these AUVs that we have already talked about. The drawback here is that as the world is changing, you intend every machine to, you want every machine to become more and more intelligent. So with this architecture, AUV cannot make intelligent decisions because payload data is not, there is no feedback. Okay? It is not processed on board. The payload data in this particular architecture is not processed on board. So in this architecture, only the navigation data is sensor, that is processed, and then it is communicated to the Neptus or the main planet. AUV must send the data before identifying. So what happens in this architecture is that you say you do the survey for a few hours, 2 to 3 hours. Okay? You search for a mine, let us say, in an area of say 3 kilometers by 3 kilometers. You have searched extensive seabed mapping. You have done. You have stitched the images and complete map data you have collected. And you after the mission is completed, you surface and you send the complete data through communication system, either wired after recovery on board the mothership or through wireless. Wireless means it will take a lot of time. It's little impractical, but still. Let us assume that the data is now communicated back to the operator. Now the operator has to spend again hours in identifying any object that he was specifically looking for, let us say a mine. So again, he has to replay the complete thing. And so this is not a autonomous system. Okay. So then what people are doing now is to implement deep learning. So deep learning algorithms such as recurrent neural network, long short-term memory, transformer module. Even I am completely ignorant about these things. So these are what computer science engineers will be working on. These algorithms aim to predict the, okay. See, these algorithms are used, machine learning algorithms and deep learning algorithms are used for multiple purposes. One is that payload data processing. Other thing is to predict the next state of the vehicle, your own vehicle. Like we talked about the navigation data and obstacle avoidance. So that is all depending on what comes next in the present situation. So sonar is looking for any obstacle. If an obstacle comes, then it will take an evasive action to maneuver. So what happens there is that you are not anticipating an obstacle. You don't know whether an obstacle is there or not. So some amount of energy and resources are spent in navigating or maneuvering around and then coming back to the original mission. So what this kind of deep learning techniques they do is that they learn from their previous experiences. Okay, for example, you are mapping the same area again. You know that an obstacle is likely to come around a particular time series or after a particular event. So based on which you can actually anticipate, okay, an obstacle is going to come. So the mission can be planned, or in real time, the AEV plans so that optimally you can navigate around the obstacle while executing the mission. Huh. So this is what I think already we spoke about what is written here. So this is the proposed tool chain for that. So on board, we will have another processor based on Jetson, which they call as a Dune slave. Basically, it is a second system apart from your main OBC or onboard computer, which will run this AI algorithm. Data processing will be done on this card. Computation vision deep learning is basically the sonar data time series deep learning. And then you do the sensor fusion from basically the sonars as well as the other your own navigation sensors. And then the target state is reported to the subplanner. Okay. Here, again, you give feedback to the plan supervisor. Okay. So the vehicle supervisor, depending on your onboard processing, it takes real-time decisions. You can see there is a lot of additional communication that is happening, decision making and additional communication that is happening within the vehicle. So this is what is at present, and it is being implemented in almost all the present AUVs, if not in navigation, at least in payload data processing, particularly image processing of sonars. So when you deploy an AUV today for mine detection, it will not wait for 2 to 3 hours. While the AUV is on the fly, in the background, there will be a low fidelity because of the onboard power restrictions. You cannot have a power intensive system. So you have a low fidelity processor running, which will do the image processing at a course level, maybe. And then it tries to identify mine-like objects or any other target of interest. The moment you get a number of such systems, based on your preset, you report immediately to base that I have seen something like a mine. So then what happens is that the operator takes a decision to do a resurvey and then get finer images of the area, or he takes decisive action that something like I have full confidence in my AV, something like mines have been detected, so let us avoid the transit lane, etc., etc. So this saves the operator's time. Of course, the bulk data will anyway be transferred after the mission, and the operator may rerun it. That is another part of the story. But in real time, you are getting intelligence and information. So this is that proposed architecture and example for the sonar processing, which I just explained to you. We'll not spend time here. Okay, so now suddenly I place this slide. We have been speaking about AEV. What is the naval architect's role for AEV development? So I would honestly say a naval architect for AEV development is not a necessity, but provided that you equip yourself with the right know-how, skill set, and tools, you can be an asset to the team. So then what do you do when you are in an AEV team as a naval architect? So you can give your expertise in naval architecture in configuring the vehicle, designing the vehicle configuration, okay, configuring the vehicle from the user requirements and designing the vehicle, and also helping to maintain and manage that design throughout the design cycle, starting from the development, the trials, and the operation. So this is one major role that so here a lot of system engineering practices come into picture. I'll try to cover it in this section. Hull form design. Hull form design, again, hull form design of propeller or the complete propulsion plant. Okay, propulsion plant, a lot of electrical systems come into picture, but still naval architecture has some say in it. Design of control surfaces. Control surfaces in most of the AVs are either rudders or tunnel thrusters. Very few AVs use vectored propulsion or the gimbal propulsion, wherein the propeller itself is able to steer. They're called steerable thrusters. But very few of them have. Most of the AVs maneuver using control surfaces such as rudders or thrusters. Thrusters will consume more power and will create noise. So most of the AVs you can see made out of rudders. So this is where a naval architect who is working in the area of hydrodynamics, okay, he can give his expertise in this area. Then, of course, system engineering techniques. I'll. It's a complex project. An AUV system is a system of systems. So, system engineering techniques are quintessential in ensuring that there are no major defects, or while you go along the process of AUV development, there are no setbacks, major setbacks. And then simulations. Simulations require a good understanding of the programming softwares like Python, MATLAB, etc. But still, naval architects can attempt, but I would not say that naval architects can themselves complete it. But they can assist in this area of simulations. And if CFD is being used for evaluating the performance of the hydrodynamic performance, there is another area where naval architects can uh, contribute. Design optimization. Of course, if you know optimization techniques, you can utilize your optimization techniques for optimizing the design during the development of an AE. Now, a few slides we'll spend on design process. Okay, so this is what happens in the design process. Basically, the user gives the requirements. They are called top level requirements. From this, along with the user, you have to define the concept of operations. Means, how are you going to operate the AUV from the mission planning stage to the execution of mission and recovery of the complete thing you have to picturize. Only then you will be able to design a vehicle system properly. So from this concept of operations, you derive the technical requirements. Concept of operation is mostly like a scenario. It's like a script for a movie. It's a story with pictures and times, etc., etc. But there are some guidelines for making it. I'll try to cover that quickly. And then you derive the technical requirements from it. Technical requirements are meant for the subsystems. I need such and such motor. I need to move at such and such speed. Okay, so then I need such a thruster. I need such a propeller configuration, for example. So technical requirements, once they are defined, you move into concept design. Concept design is where you conceptualize the configuration. You do trade-off studies. You weigh various options, and you finalize a concept. From the concept, you move on to developing the configuration. Configuration design, people call it with different names. I would like to call it as a configuration design. You develop the configuration. Once the configuration is sort of frozen, you go into the detailed design. Detailed design is where you spend time on subsystem development. You detail, for example, motor I said. So what kind of motor? These things will be overlapping with the concept and configuration design, but then you really go into the detail, minute subcomponent level of the subsystem, not even the component, subcomponent. So this is as you know, it's a kind of a spiral process wherein you refine your. This is from NASA System Engineering Handbook. It's a very interesting handbook which I followed for the design process. Yeah. So what it means is that as you have to go through several cycles, and then the clarity and resolution improves. So coming to the top level requirements, you get the strategy objectives from the user. Okay, then you identify the enabling technologies, what can achieve this strategic objectives. You see what is more important is that you cannot dream of any hi-fi technology because it may not be ready. So that readiness levels and technology gaps you have to identify. So in certain projects, what we do, we develop a system, and where there are gaps, either we try to acquire it from somebody else, or we try to parallelly develop the system, or it may be for future gap filling also. And then you take a global scenario assessment. What are the systems available across the world? You study them. You carry out an analysis of the user requirements, and then you define the success criteria. So this is what happens in a top level requirement. Concept of operations, you give an operational overview. What are the major phases of operation? Operational scenarios you bring out. Means what are the various scenarios in which the AV is going to operate? What happens? So this is all stories and ifs and buts and logical actions, etc., etc. You try to make an end-to-end architecture. So this, in fact, end-to-end architecture was recommended by NASA System Engineering Handbook. This helped us a lot in configuring our AV. And then you work out the communication strategy, timelines, critical events, and risks. So these are the important things in the concept designs. No, I mean the concept of operations. Coming to technical requirements, you allocate the requirements, you capture the requirements into your database, classify it, and then you decompose these requirements. So again, this process identifies what must be achieved by the system at each level to enable a successful requirement. So here, the product one method is product breakdown structure. What I showed you in the first slide. You identify what is going to be your product, or you make what is going to be a product breakdown structure. You do a functional analysis. So one effective tool is functional flow block diagram. Looks this is product breakdown structure. This is level one. So AUV and the major systems. Then you can go into different levels. This is level two. You take navigation and guidance, navigation part and guidance part. What are the systems coming? Again, you go to level three within INS DVL or within the front-looking sonar. What are the components? So this keeps on growing as and when you go to the next spirals. This is the functional flow block diagrams. Again, there are levels. So this first level is the various phases of the mission, and each phase is then expanded. Okay. For example, while executing the mission, you switch on the sensors. So this is all English, and then logics. Again, each of this is expanded. So this is how we functionally evaluate the requirements and arrive at a configuration. And then you move on to the once these things are clear, you might have already started the concept design, but again, these all overlap, and it comes to a convergence at some point of time. Okay? So you define the concept, design alternatives you see. Okay? For example, these are the various design considerations and design alternatives that can come to your mind when you're configuring an AUV. Hull form, what kind of hull form I should choose, what kind of propeller I should choose, what kind of rudder, navigational sensors, communication systems, etc. Then you do a trade-off study. So trade-off study, there are various tools available. Like you do brainstorming, very effective tools, brainstorming with your team, outside your team, with experts from the industry, international teams, experts who have already developed such systems, gives you a lot of help. Then there are some system engineering techniques like Q metrics, wherein you try to rank the options based on their merits and demerits. QFD, quality function deployment, house of quality, sort of thing. It's a QRS technique, system engineering, a very effective tool for carrying out trade-off studies. Then you do a feasibility study, whatever you have conceptualized, whether it is really feasible to realize it and offer it as a product. Also, you identify the risks and mitigation plans. So this is what happens in the concept design stage. Now, once this phase is over, you go into the configuration. So here in the configuration, of course, as a naval architect, you will populate and make a general arrangement. And with the available tools today, we always go for a three-dimensional CAD sort of arrangement. We can call it a walkthrough model or whatever, but it will be a three-dimensional sort of a virtual assembly line wherein a complete three-dimensional model of the AUV is made with all the subsystems, even up to the nut bolt level, can be made at this stage. Not very difficult. You just there are very powerful CAD softwares available today, and then you have to estimate preliminary vehicle characteristics. So here you cannot spend because your design is not frozen here. Okay. Please remember that these are early stages of design. So you need cost-effective and quick estimation of preliminary vehicle characteristics. So you need only approximate estimates to just ensure that you are doing the right thing. You cannot spend your resources and time on, say, time-taking and expensive solutions like experiments, or even CFD is not recommended at this stage. Because it's, okay, you can go for a, what do you say, low fidelity CFD, not the RANs or anything. If you have any custom-made numerical approximation techniques, you can use them. So the profile, for example, miring profile is a very commonly used and very aerodynamically very effective profile, which has been used for almost all kind of axisymmetric hull forms. And there are sub of models. So DARPA, these are some of the examples of axisymmetric configurations which people use extensively for AUVs. Already people have done the research, and so why do you reinvent the wheel? Unless you have some specific requirements where you have to place certain sensors, etc., etc., you don't go for a new profile. Or you should have a parent profile with you, which is already evaluated. And then propeller, you select a suitable propeller, or you buy an off-the-shelf thruster, or people even customize their thrusters. And the next, before selecting the propeller or going for finalizing the battery or the energy source of the system, you need to estimate the drag. So there are various methods available. Two of the it is my personal choice. Shabra method and DATCOM methods I find very close to actual results. Though there are many other results. I mean methods which people use. These are all empirical methods. Okay? These are all empirical methods, but very effective for initial estimates. And when you talk about powering, you assume a QPC, overall propulsion coefficient of 0.6, which is a very conservative. Conservatively, you take a 0.6 efficiency, overall efficiency, and estimate the delivered power. This will be an input to the propeller designer as well as to the you can tell your battery person how much power you require for the propulsion part. Similarly, you do for the payloads as well. In an AUV, the propulsion and controls take a major part of the battery power, and then of course the payloads also consume power. So this calculation can happen in the background. Maneuvering and control. Published literature is available on Rema's. Rema's beautiful publications are available for the 6-dock model and the even the control part that is used, ECA9, LAEV, all these are published. You can use either one of these, or if your AV is not axisymmetric, it has a sort of a submarine kind of shape, you can go for Pellman's model. So this is another option. Then you carry out a sort of a linear stability analysis and to confirm the sizing of rudders. Okay, you might have done a preliminary sizing of the rudders. You can do a quick estimate of these hydrodynamic coefficients. Not all of them, only what is mentioned here. So using this, you can actually evaluate whether your vehicle is going to maintain core stability and your rudders sizes are chosen are adequate or not. And some initial estimates of the forces. Forces you cannot estimate here. So some other coefficients. So these are the different methods for estimating the hydrodynamic coefficients. They are well established. You can refer to any of these. And some other coefficients are there which are not accurate. You may ignore them in the initial. Let it be only an approximate estimate. And then you do MATLAB simulations. Okay. Gazebo is too early for the initial stage. MATLAB simulations are good enough. So Fossen gives you a good idea, or even MATLAB ready-made toolboxes are available. Traditionally, we used to use either MATLAB code or Simulink for executing the various trajectories, just to confirm that whatever you have configured, hydrodynamically it is a stable configuration and it is having the required maneuvering characteristics also. Rudder design, already you might have done the design, choosing a suitable NACA series, simplify it initially, go for the fine tuning at a later stage. Weight and buoyancy, you take sufficient design margins. This is very important because in the initial stage, you may not know the weight of many of the systems. So it may take you maybe 1 year down the lane to exactly know the actual weight of the subsystem you are going to include in your vehicle configuration. So here you need sufficient design margins, and then you cannot over design also. So a good approach is to go for probabilistic estimate of the design margins. You can use Monte Carlo simulations. This paper gives a good story about how they determine margins for spacecrafts. Okay. Now coming to detail levels, the detailed design. You have to define the environmental specifications and reliability aspects like the mean time between failures, etc. Okay, let us not go into details. It will not be useful to you. Then you finalize the subsystem specifications. You undertake using the specifications, the detailed design of systems and technologies. You plan for design validation and execute it. So here you go into executing CFD, finite element analysis for your mechanical structures, strength calculation, CFD mainly for your hydrodynamics, maybe for your other specific systems also to whether a particular protrusion like an antenna is not creating disturbances, etc. flow around the sonar. All these things can be evaluated using a CFD. You undertake simulations like we saw earlier in MATLAB. You go into more sophisticated simulations like you have a gazebo-based simulation wherein a physics-based engine is used in order to simulate your actual vehicle movement. At a later stage, you can actually make prototypes and do experiments in a hydrodynamic test facility like a towing tank or seakeeping basin. And you actually make the prototype. And if it is a smaller AUV, directly make the AUV, take it to the field and tune the coefficient. That's also very well accepted. That's what smaller AUV manufacturers do. They don't invest on experimental or okay. I think somebody is unhappy with the presentation. Okay, I'll try to make it more interesting. Prototype manufacturing and testing is the next stage. So this is where you come towards the realization of the prototypes. The subsystems are developed and, at various places, and then they go into testing. And there are some other aspects like acoustic characterization and noise management, thermal management of each system. Okay, this is very important from because this is a closed environment, and particularly inside pressure hulls, this processors and your power distribution systems, all these things will be dissipating heat. It should not be affecting each other. If your system, if your enclosure is in contact with water, there is not much of a problem. Through conduction you can dissipate, but still thermal management is to be taken care of, particularly for long endurance AUVs. Acoustic characterization becomes important because we will be using multiple sonars, particularly for low frequency sonars. It is of great interest. High frequency sonars, it doesn't matter that much, but low frequency sonars get affected by the acoustics around the body, the noise that the vehicle subsystems generate, as well as the flow noise. Of course, design optimization. Already we spoke about it. Now coming to development, this is perhaps the last stage in configuring an AUV. So the various major systems I have just, for example, shells. You may have a doubt as a naval architect, what are the materials used? So either you make out of aluminum. Aluminum is most commonly used for larger AUV systems. Mild steel is hardly used. It's not used except for maybe for XLUVs or something. Titanium is of course very costly, except for specific uses like deep, very high depths of use. Titanium is avoided because it's very costly, and CFRP is very commonly used, particularly for smaller AUVs. And plastics are being smaller AUVs are being made out of plastics nowadays. Delrin is one good example. So these are manufactured. If it is a metal, it is mostly by machining. If it is plastics, it is normally by molding, and the sections are joined by either welding in case of or bolting. And wherever for watertight integrity, we use O-ring seals, and pressure tests are extensively done during the development to ensure that they withstand the underwater pressure. So if for every 10 meter of depth, 1 bar pressure increases, as you know. So if you talk about 100 meters of depth, operating depth, you are talking about 10 bar pressure. So this pressure testing, external pressure testing is done on the shell first in order to ensure that there is no leak. Subsystem development happens at respective OEMs or industry, and then environmental tests are carried out once these subsystems are developed to ensure that before going into the marine environment, these are able to withstand those kind of environments, or within the structure of the AUV, it is able to withstand the environment, whatever it is being exposed to. There is some, once these systems are developed and these ETs are completed, you subject it to something called hardware in loop simulation, wherein without the actual platform, you link up all these subsystems, and with some software assistance, you simulate an environment in which an actual mission is going on, and whether your motor is able to run or your actuation system is able to deflect the rudder. This is mostly done in air, in lab condition. So this we call as HILS, hardware in loop simulation. And maybe a turntable can actually rotate your INS and give the impression of that the vehicle is taking a turn and all that. Your mission computer system will be running all the time. So this your control algorithm is tested. So this the hardware as well as the software is tested during this activity. And then you progress for the assembly and integration. Here, the weight of the vehicle and center of gravity of the vehicle. These are two major aspects from the hydrodynamic perspective. So the designer and the developer has to be very careful to manage the weight. You cannot afford the practices that we do in the shipbuilding industry, where weight often process exceeds the limits. So here, if that happens, then the AV cannot save. This is very meticulously done. Then we once the integration is done, okay, before closing the vehicle, we do something called bench checks. So this is very commonly done. I think all of you know that. You run the mission sequences multiple times in the integration day. Finally, box up the vehicle, and then you do the leak checks, and then it's all good to go. So this is how an AUV is configured once the initial development is done. Yeah, I think it is 540. Dynamic math model, I will try to quickly go through because time, I think we are running short of time, right? So AV dynamics is highly nonlinear, coupled, time varying, and subject to hydrodynamic uncertainties and external disturbance. So the design of a control system is essential for trajectory tracking. So here you try to control the yaw, pitch, roll, speed of the wheel. For this, we need to develop the overall mathematical model of the wheel. It's already developed, but I just explained to you about the physics of the mathematical. So here, interdisciplinary study of kinematics, hydrostatics, and hydrodynamics is involved. Then we all know hydrodynamic coefficients. I believe all of you have done your courses on hydrodynamic coefficients. So these are very important part of your AV dynamics, and this should be estimated properly. So the dynamic equations of motion, these are highly nonlinear and coupled due to hydrodynamic added mass, lift, drag of the vehicle, the Coriolis and centripetal forces. And another thing is that these include uncertainties. So that is why estimating them with minimum amount of uncertainties are very crucial for your initial development. So these are the assumptions that we take while evaluating the dynamics of the body, that it is a rigid body of constant mass. Okay, Earth's rotation is negligible for acceleration components of the vehicle center. The primary forces that act on AUV are inertial and gravitational, and they act at the origin. So origin can be at the center of buoyancy or at the geometric center of the body. It is a designer's choice. Generally, we don't keep it at the CG because CG keeps shifting based on the configuration. We can even keep it at CG, but again, we have to keep on changing CG each time. Yeah. So as you know, the AUVs are capable of 6 degrees of freedom. Autonomous underwater vehicles or any underwater vehicle is capable of 6 degrees of freedom, wherein 3 translational motions come and 3 rotational motions come. So here we follow a right-handed and a rectangular coordinate frame. This is a body fixed frame, and then there is an earth fixed frame. There is one more frame called a moving frame, which is parallel to the earth fixed frame. Okay, your body orientations are measured with respect to the earth fixed frame, and then you have to translate it to the body frame, even the translational motion. So this is the notations that we use for surge, sway, heave, roll, pitch, yaw. These are the forces and moments, and then these are the linear and angular velocities. These are the positions and Euler angles. And this is a SNAS notation, just giving you as a brief introduction. So these are partial derivatives. Okay, these are nothing but these are what we call as hydrodynamic coefficients. So if I tell xu, it is nothing but dou x by dou u. This is the symbols and notations that we are going to use. So coming to so what we said is that the axis that is fixed in the earth, whatever you are measuring, you should translate it to the body frame. Now here you use a concept called Euler angles. In certain other domains, I use quaternions, but for our underwater applications, Euler angles are sufficient. So phi, theta, and psi. Phi is for roll motion, theta is for pitch, and psi is for yaw. So this follows a Z by X rotation sequence or 3 to 1 thought. Okay, so this is if I'm not going to derive this or anything. This you can study at your leisure. This is the transformation matrix, which can be easily derived. You can do this as an assignment or an exercise. Easily you can cover that part. A transformation from global to local velocity vector is done using the transformation matrix. Once you know the global velocity vectors, you translate it to the body frame. And once you know the global angular velocity vectors, you convert them into the rates of local frame, body frame. So this is the sixth-order nonlinear dynamic equation of motion. MV is the inertial matrix, including the added mass. CB is the matrix of Coriolis and centripetal terms, including the added mass. dV is the damping matrix, and Geta is vector of gravitational forces and moments, and tau is the controlling force. And here V indicates the transpose of the velocity. Now, let us talk about deriving the coupled equations of motion of AUVs. So here we will use, there are two approaches. One is the Lagrangian approach and the Newtonian Euler formulation. So here we'll use the Euler approach because it is, the other one is based on energy. This is much more, what do you say, straightforward, or you can, easier to handle. It is, you apply Newton's second laws of linear and angular momentum. D by dt of mv and d by dt of h. So here h represents the angular momentum, m represents the sum of all applied moments, and f is the sum of all externally applied forces. B is the velocity vector. Now here it is convenient to regard it as a sum of the equilibrium point as well as a perturbation component. Okay. So here the equilibrium points becomes 0 because equilibrium means it is vehicle is moving in an unaccelerated motion along a straight path. So during this motion, the linear velocity vector is invariant and angular velocity is 0. So therein this can be simplified and made into this term. This is the transpose of the, in the Earth fixed coordinate system. So once you simplify this, yeah, the force equation based on the rate of change of velocity relative to Earth fixed frame is given by, it is again differential of mass into velocity. So this can be written as a combination of the body frame plus the angular momentum, angular velocity into the mv in the Earth fixed coordinate system. So expanding this, you get forces in each axis, fx, fy, and fz. You can call it as capital X, Y, Z, and you get mass into u dot plus uw minus rv. So this is same for each axis. From here, you get the translational acceleration. Now, similarly, after transforming from the body fixed frame to the Earth fixed frame, the moment equations you get. So here you simplify because if the AUV is symmetrical along the x, y, and y axis planes for most of the vehicles, the moment of inertia has become 0 in the ix, y, z, x, z, in the matrix, only the diagonal terms remain. So here you can simplify your moment equations in such a way. I know I'm not doing justice to this because it is very difficult to cover this in a 1 hour lecture. Rotational accelerations can be identified. Derivative of Euler angles also finally you get. So then comes the gravitational forces. So gravitational forces, only the forces are there. There are no moments. The force equations come. I'm not again going into the details of it. You can read it. This is all available in multiple literatures. Hydrostatic forces and moments. So here again, you get the weight and you bring in the buoyancy part also. Whenever a vehicle body is floating or submerged, the buoyancy component comes into picture. So instead of the just the gravitational part, you bring in the buoyancy part also into it. And then the orientation also you bring into the part with respect to the gravitational force vector. Then hydrodynamic forces and moments. So this hydrodynamic forces and moments estimation is perhaps the most important part of this complete mathematical model. So it depends on the given shape of the AUV, and it will be unique. These can be estimated based on either one of the following methods or a combination. So empirical or statistical you can use. CFD, experiments, field trials. Field trials, of course, will be the most will give you the most accurate feedback. But again, we need to wait until the prototype is developed. Now coming to when I cannot skip this topic without talking about added mass and inertia. All of you know what it is, but I'll just touch upon that. Added mass is nothing but the pressure-induced forces because you are accelerating in a medium in forces and moments. Okay, due to the forced harmonic motion of the body, and these will be proportional to the acceleration of the body. Okay, because water has a significant density. Okay, when a body is accelerating in water, there is a reaction force due to the additional inertia of the fluid surrounding the body. So this is accelerated by the movement of the body. And then this is a function of the body's surface geometry. Again, it depends on the shape of the body. Yeah, the inertial matrix is not necessarily positive definite because of this point. And then coming to the propeller, the thrust and torque. So thrust and torque is generated by the propeller. Propeller, as all of us know, it generates a thrust. Along with it, it generates torque also. This torque will affect the roll imbalance of the vehicle. So this will act along the x direction, and also the torque will act about the x-axis. So these terms will also be reflected in the equations of motion. Now, combining overall the nonlinear equations of motion for the AUV in 6 will be like this. So here you can see all the terms are covered. So this XU dot, YV dot, YR dot, ZW dot, ZQ dot are all added mass terms. XUU is the axial drag. The YRR, YV, ZWW, ZQQ, these are all cross flow drag terms. This is a propeller thrust. These are the terms, and there are some rudder lift terms coming into picture. Monk moment and the added mass terms, and the that is coming in the moment equation. Yeah, it comes in the MUW term. So these are the moment equations and these are the force equations. So this is the complete mathematical model of the vehicle. This is what you use to create the 6-DOF model of the vehicle. So your aim in this entire exercise is to estimate all these hydrodynamic coefficients using various techniques. Now, once you identify and create the model, these are nonlinear differential equations. Okay. Now they are complex, and it is we can solve it using numerical integration. So usually we use Rangakuta method, second order or fourth order. Fourth order is used mostly nowadays because of the compute power available. And this is done using tools such as MATLAB. Okay. Traditionally, we have been using MATLAB codes, Simulink based, or any other advanced simulators. So now coming to the chapter 4 of this particular section. First of all, why simulators are required? The field trials of AUVs are expensive and laborious. Okay? So cost is involved, the resources are involved. You need platforms for deploying AUVs. You need people are involved. Okay, it's an expensive affair and laborious affair. So you need to minimize likely errors that can be identified and corrected. So if the errors can be identified and corrected upfront, it will save a lot of this your resources and time, and improve the mission effectiveness. When you do simulations, it is in a lab. So in a lab environment, when you do simulations, when you're able to accurately simulate or replicate your actual vehicle using a engine, you can actually plan your mission in a better way. So the AUV simulator with realistic vehicle dynamics and simulated sensor, navigation and control systems will immensely help during design, development and operational stages. So several simulator architectures are available, among which many are open source. So it's a very good thing. So that is why this is helping AUV developers across the world, and these are being widely used because this aids people like anything. You don't need any infrastructure for it. You just need a good computer system. Single laptop is sufficient. And of course, connectivity to the internet, because everything is on the cloud. You just download the libraries, and so this is. I'll just briefly touch upon various simulator platforms available, particularly MATLAB. This is not an open source. This is a paid, expensive software. So, but it gives, it's a well-established engineering software. So, with Simulink and Simscape, the physical modeling can be done with Simscape. This is a screenshot of the MATLAB toolbox for AUVs, and Simscape multi-body for integration of hydrodynamics, fluid effects, dynamic behaviors, and inertial effects from the CAD models. And Simscape electrical toolbox can be used for building models of vehicle subsystems, and you can use it to simulate component failures, evaluate subsystem level performance. With Simulink, again, you can connect the plan models to low resolution cuboid environments like this, or photorealistic worlds, like a realistic underwater environment in Unreal Engine, to simulate sensor behavior. validate perception algorithms, and present your results. So this is an example of the trajectory that the vehicle has taken. You can just verify it as per plans. So this is was commonly used, but nowadays gazebo is being used by left and right way people because it is much more realistic and sophisticated, easy to use, and open source. So there is no cost in it, absolutely no cost in it, except for the hardware that you are buying your laptop. So gazebo environment with ROS middleware. This is again from University of Photo. Sorry, not from University of Photo. ROS is from I think MIT. Gazebo is an open source 3D robotic simulator offering realistic simulation. Okay, Gazebo is in fact used for various engineering simulations or particularly robotic simulations. We can use it for AUV simulations. So here we can use it for realistic simulation of sensors and noise models of sensors, advanced 3D graphics, and the physics is precise. So it uses an engine called DART. The framework is like this. Gazebo, you have a physics engine, then a graphics engine called AUVs, and the simulation. And you use something called a ROS. ROS is nothing but robotic operating system. It's a architecture with various nodes for autonomous underwater vehicle or robotic application. So these nodes have sensor modules, control and navigation aspects. And another good thing about Gazebo is that earlier we discussed about Dune and Neptus. So it can be integrated with Neptus using a bridge. So this is some screenshots of Gazebo simulation for an AUV. Very realistically, you can simulate the actual environment and you can actually plan the mission, preset your sensors. Even you can see the sonar field of view, how the sonar is detecting any scanning the sea bottom or detecting the target, how effectively it is able to plan, execute the mission, the maneuvers, the maneuvering characteristics. Whatever you're actually doing in experiments can be much effectively if you can visualize here. So this is a very powerful and useful tool. These are other simulators. MOS is a Python-based simulator. So again, for Gazebo, you need to have a good knowledge of Python. That is a prerequisite. And MOS is also a Python-based robotic simulator. Underwater sim and UW sim and subsim, these are also engine-based simulators. So these are some of the AV simulators, and without simulation, I think nowadays nobody can think of an AV design and development. So let us move on to the section 2. I think we will be finishing in another 10 minutes. So these are the challenges. I feel the biggest challenge, though we have been calling AUVs as autonomous underwater vehicles, it's a misnomer because they're basically automated systems. Because I've been telling you, we are pre-programming the AUV and then deploying it. Okay? It is not the real-time decision making based on situational awareness is very minimal. Very recently, AUVs are coming up with onboard processing techniques because hardware is available. You have the single board computers, Jetson cards, etc., which has that in that compact form factor and low power. It offers you compute capabilities. So now people have started using it for implementing decision-making techniques, including using artificial intelligence and machine learning. So wherein the AUV is able to take real-time decisions. So if you see, autonomy is defined as the ability of an entity. It's a beautiful definition. Entity to independently develop and select among different courses of action to achieve goals based on the entity's knowledge and understanding of the world itself and the situation. So basically, it has to have some knowledge based on some previous experience, and it has to understand the world itself and the situation. So based on that, it has to independently develop. So these are all very keywords, independently developed. So whereas if you look at traditional AVs, we have been pre-programming it and then sending it to sea. They're all automated systems. So the challenge is to migrate to this autonomous systems. So here, one key difference is that autonomous systems are governed by broad rules that allow the system to deviate from the baseline. Even if you say that you go in a straight line and take a turn and come back, it can actually deviate from it based on its intelligence. Whereas automated systems don't allow for deviations. Okay. So this is the ongoing challenge, and people have already started implementing the challenge. Another challenge is that the sensors underwater don't perform as well as in the ground environment. Okay, that we'll touch upon. So the input for any AI AML, this thing you need data. So the data that is coming in has a lot of noise. So this is one other aspect of difficulty that we are facing. Now coming to communication. Communication is another critical aspect which we should improve in order to make AEVs, autonomous systems, more effective. So here, require robust communication facilitation with the satellite ground station. So AEVs will be at long ranges, it will be communicating with the satellites, and at line of sight, it will be directly communicating with your base. It can be a ship or a ground-based system. Here, we are limited by bandwidth. Okay. Only in very close proximity, Wi-Fi works. You get high data rate so that you can transfer some bulk data. It will be in GBs. So when you run a imaging sonar for say 1 or 2 hours, the important process data will be in GBs. If you if you run it for number of days, it will go to TVs. So you cannot imagine transferring it wireless. You have to actually recover the AEV and then plug in a physical cable and extract the data. So without recovering the vehicle, because recovering the AEV is the most difficult part of the entire AEV operation. As far as the physical handling part of it is concerned, it's very dangerous and very risky. Picking up something from sea from a mothership, given the sea environment, we'll talk about it in a couple of slides later. So here, acoustic communication already we discussed, limited by range and bandwidth. So once this communication is extremely essential in order to keep track of the vehicle and periodically report exchange of information at long ranges. So these have to tremendously, localization and track. So as all of you know, when you navigate your car, it's very comfortable nowadays with the 5G system network and your GPS. You can go anywhere in the world. What is there in the map? Okay, so whereas GPS doesn't work underwater. The moment you dive down, there is no GPS. So you have to work on dead reckoning. For dead reckoning, you have to use inertial navigation systems. So which can be a small AHRS attitude heading reference system or an IME for small AEVs or a sophisticated system for high endurance vehicles. And the issue here is that the INS actually has some gyros which will estimate the accelerations. From there, it integrates to get velocities. Again, it integrates to get the position. So over a period of time, the error in this integration processes increases. And then the drift in the position speed, though, it will be drifting from initially itself, if we talk about INS. Increases like anything and your localization collapses. So you may think that you are at point A, but you will be far away at point B if you run for number of hours on pure inertial mode. So you need some aiding. So this aiding is done by equipment such as Doppler velocity log, which works on the principle of Doppler. It sends a sound signal and it reflects back and it estimates the platform's relative velocity with respect to the environment. So this goes as a feed. So instead of integrating from the acceleration, we directly have a velocity feed. So you have to do only one integration. So therein you reduce the positional drift. So this is what you may target to reach Karachi, but you may end up in Chabahar if you stay underwater for a long time. So what AEVs typically do is that it surfaces periodically, maybe in a predefined interval, say a couple of hours time. It surfaces. It has a GPS antenna on surface. It takes a GPS pass, takes a GPS feed from the satellite and corrects the navigation. Okay. So, and these systems, if you go for sophisticated navigation systems, again, they're very costly. So this localization and tracking is a challenging, but it is implemented. It is a challenging. And nowadays, people are using various localization techniques, trying to use at least like simultaneous localization and mapping. People have been talking about it for a long time, but implementation level, how much success they have at a commercial level. That sensor fusion is another thing that we have to talk about. Multiple sensors input has to be fused. in order to get our own position localized. Sonar vision. See, underwater electromagnetic waves attenuate rapidly, and hence, if you are using camera systems, you can hardly, the best camera may be able to give you some range like 10 meters. So we have to rely on sonars for navigation as well as long range imaging. So imaging sonars are particularly vulnerable to vehicle motions. If there is a disturbance, roll pitch disturbance, or there is a heading change, then the image quality rapidly deteriorates. This image that you see here is a side scan sonar image of the sea bottom, and this is one of the best images. So the typical images will be much more bad. So if you are looking at a mine or something, you'll be seeing something like this, and then you have to zoom in and manually, if you're seeing, you have to zoom in. So this is where the image processing algorithms have to work. So, if you're talking about low frequency, this is an imaging sonar. They are typically high frequency sonars, but their range is limited to say 100 to 200 meters. That is a typical range of a high frequency imaging sonar. So here on land, you can, if you are doing an aerial surveillance, you can see kilometers. Whereas underwater, see, look at the ranges that you can actually picture. And then low frequency sonars, of course, for detecting submarines and all based on the acoustics, noise signals. It can give you up to practical ranges of 2 to 3 kilometers. On paper, higher ranges are promised, but practically this is what you get. Yeah, other practical issues are, as far as India is concerned, as I already pointed out, all these sensors and the vehicle subsystems used in an AUV, they're very compact and of low power systems. And it has to be efficient, fault tolerant. Such reliable systems are lacking in the country. Okay. So here, lack of indigenous sensors means you have to always import the systems. Imported systems, cost is more. Once you buy the system, it becomes a black box. Any issue later, you have to fall back on the OEM. Becomes costly. Maintenance is costly. So this may be one of the reasons why AUV is not that popular in the country, in our country like India. Whereas if you look at the US or Europe, AUVs are extensively being used because they have, every country has a base of industries that supply chain and collaborative approaches, everything is there. And it is data driven. So you need a lot of data in order to fine tune your vehicle, fine tune your missions. So each time you have to spend more time at sea, basically. This consumes resources, and trials are resource intensive. Launch and recovery is a nightmare. Putting something into water, launch is relatively easier, but recovery is extremely difficult. Many a time accidents happen. You tend to lose the vehicle because when you have deployed the vehicle at morning, say 6 o'clock, the sea state was very calm, very nice sea state 2. And by the time you recover the vehicle around 1 o'clock, sea state has become 4. Okay. So you are able to see the vehicle floating, but you are unable to pick it up. The ship is dancing, and many a times it hits the ship, or due to some reason the vehicle is lost. Accidents are very common. Maintenance, as I said, maintenance of these sophisticated sensors have to be. There has to be a trained manpower who has to, cater to the operations as well as maintenance of the. So it becomes expensive, but these things will become more affordable the moment the user base widens. That's what I'm trying to say. In India, we don't have a user base that we have to create. So this is we move on to the last section. These are the emerging trends. Okay. The last but second. Okay? One more section is there. So this is the global naval ecosystems. I just want to say this is a picture taken from Pentagon Unmanned Systems Roadmap. US has been, they're the first country to develop and deploy an AUV, 1957. So they have a plethora of industries who are developing autonomous systems, and they are being extensively used even by the US Navy. Large amount of systems are being used, and globally, we are seeing the use of unmanned systems, and particularly in warfare. In the ongoing warfare, you can see sophisticated and unsophisticated means of unmanned systems being used. So these are the 4 major aspects of where evolution of unmanned systems take place: interoperability, autonomy, network security, and human-machine collaboration. So this, I'll not go into details. This is more about the autonomy part. And this is the roadmap. Yeah, okay. So here some interesting things are there. Artificial intelligence and machine learning. It is expected to evolve, and the forecast by Pentagon is 2042. The AUVs expected to become highly autonomous with all the capabilities of persistent sensing and whatever we spoke till now. Swarming. If people are speaking about swarming, but what is happening right now is not actual swarming. Is what our swarm team says. Our project director for swarm team says, which is right in saying that because swarming needs communication. With limited bandwidth of communication, swarming cannot happen. What happens on ground cannot happen underwater. So what can be achieved is maybe a leader follower approach or cooperative control of the vehicle, cooperative navigation. That can happen. But in theoretical sense, the actual swarm, like how a swarm of bees behave with its own intelligence and communication between each other, that will take time. Yeah, trust is anyway. It's an ethical side of it. It's a long-term activity. Weaponization is anyway. People are doing, navies are doing, military organizations are developing. Sometime, yeah. This large displacement AUVs. So traditionally, we have always been seeing up to heavyweight AUVs being used extensively. This large displacement AUVs are recently being extensively being used, particularly by navies. So these are mostly to track for covert surveillance of adversary submarines and surface ships. So this is Russian AUV. This is the Blue Whale from Israel. It's a nice AUV, very nice AUV. It is again based on the IAC Explorer series of AUVs. If you see the design, this is a Canadian AUV, which already we discussed. This is the AUV which DRDO is developing, called the High Endurance AUV. This photo was taken in Kochi. So it's a multi-mission AUV. It is capable of doing multiple missions: submarine detection, mine detection, sea surface ISR, oceanography. Just a moment to check. Yeah. Am I audible? I am audible, right? I'm not disconnected, right?
Yes, sir, you are audible.
Okay. Suddenly I got a call. I thought I am disconnected. Yeah. So submarine detection, mine detection, sea surface ISR means AUVs are intended to be underwater vehicles. So whenever it comes to surface and operates, so much of energy goes into diving back, and effectiveness reduces. It starts to roll more on the sea surface because of its inherent shape. But still, surface operations are being extensively done using AUVs due to various reasons. You use some deployable sensors for secretly listening to or carrying out surveillance on enemy platforms. And oceanography has been, it's a oceanographic sensor that we are carrying. And we also have equipment for searching for crashed aircrafts. This is another sonar, beacon locator sonar, and recording of acoustic signatures for multiple missions. So here, what we are trying to do, we are trying to develop indigenous systems, particularly the sonar systems. That's what the hallmark of this project is, that instead of buying and assembling imported thing, most of the sonar systems are being indigenously developed. They may be inferior in quality because, see, the imaging sonars and other sophisticated sonars, European countries and the US OEMs, they have been working for decades. So we are talking about last 5 years of development. So if you compare one-to-one quality, they may be inferior, but we are taking that first step, and with hand-holding all our industries, with all our limitations, we are going ahead. And the advantage is that 95% of the sensors, except the navigation sensors, that also navigation sensor also in future will be indigenizing. But right now, because of the precision requirements, we are using an imported sensor, and oceanographic sensors and other few equipments like pinger, all these things are imported. Except for that, most of the vehicle systems are indigenous. Now, extra large AUV, we have seen that champagne breaking photo. So this is the layout of that vehicle. So this can actually lay mines. Okay, so this is in effect it can be used for warfare. So this is capable of laying mines. But, we have to wait and see. Yeah, this is 26 meters long, 2.6 meters by 2.6 meters, whereas our AV is a much smaller class. It's a large displacement class, 10 meters length and 1 meter diameter, 6 tons class AV. This is a 85 tons displacement class. Okay, endurance is of the order of 45 days to 6 months. You can imagine. But the speeds, all these AUVs are slow moving vehicles. 3 to 8 knots, 10, 12 knots is the maximum speed of an AUV because it's not required. These are all slow moving surveillance kind of vehicles. Unless you talk about weapon deployment, you don't need high speed. Recently, this Manta Ray AUV, which is in the shape of a Manta Ray, it is a hybrid glider system equipped with propulsion systems. This is developed by the US Navy. It's a huge vehicle, and much details are not known, but it may be used for surveillance. So basically, we understand that it is a technology demonstrated. Beautiful looking, wonderful to see this. Yeah, this is a little bit of thumping the chest. So this is HI Sutan is one which brings out news about autonomous systems. It's an online portal. They have published a list of major world large autonomous underwater vehicles, and in which our AUV also got featured. So India is on the map. Significant feat, but we have lots of work to do with respect to enabling technologies. And previously, I spoke about the SWARM project that DRDO is handling. In fact, NSTL is a model lab here also. So we are developing 30 kg class man-portable, single man-portable AUVs, which can be deployed in multiple numbers. This will be used for surveillance. And even here, we have one class of AUVs which can be used for neutralizing the mines. So in this, there is also autonomous surface vehicles. Okay, so this will be on the sea surface, acting as a command base or for communicating with the AUVs and then to the base station. So this is again two variants. We have one is with a startup called it's not a startup, it's an MSME, Safe Automations, and GRSC along with a startup called Rekis Marine. They have also developed a variant. So these two variants, one is a monohull and one is a multi-hull configuration. So there is in Swarm, there is an underwater vehicle configuration of Swarms as well as an autonomous surface vehicle for interacting with the Swarm. It's a beautiful platform. In fact, this has a lot of features that I've been talking about, like implementing the artificial intelligence and deep learning techniques so that decision making in real time takes place. So these are some hybrid systems which other OEMs have developed. An autonomous surface vehicle deploying a torpedo. So that day is not far away where AUVs also will start deploying weapons. So this is an autonomous surface vehicle firing a lightweight torpedo. Drones are being used. Hydroid Remus recently was launched using a heavyweight drone from a aircraft carrier. So drones will be used in near future for deployment of AUVs from mother. Oh, this is a beautiful platform, Wave Glider. It's a hybrid system. It's an engineering marvel. It is made by a firm called Liquid Robotics, which is a subsidiary of Boeing. Okay, so this has a float, which surface float, which has solar panels, and it floats on the surface. It rides over the waves, and then there is a they call it a sub, which is almost shaped like an axisymmetric torpedo-shaped body, streamlined body, and this floats below. And then this can be equipped with multiple sensors. Okay, it can be used for oceanographic purposes or for even ASW operations, which you equip with the towed array sonar. So then what happens is that real-time communication with the base station happens, and it can have long endurance because it is propelled by the energy of the base. For forward propulsion, the difference in wave energy on the surface and the depth. As you know, the velocity or the energy levels at the surface because of the wave motion will differ on the sea surface as well as at the depth. So this difference in energy, wave energy, is being utilized for forward propulsion. Beautiful concept. I mean, whoever conceptualized and realized it, tremendous. So when the sub is equipped with the total, it's already we discussed. So it can be used for ASW applications, and navies have started using it. This is the way ahead. More autonomy. We need to inculcate situational awareness. Blah blah. We have already talked about it. Operational safety and efficiencies. So the expansion of capabilities from task level. It's important to have integrated human AUV teams. So this is an important concept wherein AUV and human teaming. Any robot human teaming is quite essential for the successful implementation. better communication computing capabilities, sensor fusion. Data from various sensors, for example, sonar, you're looking for a mine, you have a magnetometer looking at the magnetic fluctuations, and then you pick up signals. You need to use will improve AV capabilities. Autonomous modeling and simulation advancements, cyber resilience and robustness to cyber attacks. So the moment autonomous and network capabilities come into picture, cyber attacks are going to. Swarming and networking capabilities already we discussed. Yeah, indigenous sensor development in the industries have to be promoted, and the major it involves a lot of cost and resources in developing sophisticated compact sensors. And the main reward that you want is you need a sustained vendor base. Customer base. You need customers for your developed equipments. So in India, the issue is that the AUV market is very thin. Sorry to say this, but the AUV market is very thin. The other day, a startup who has done beautiful business in developing beautiful compact systems, ROVs, were saying that extremely difficult to convince even big shipyards and all to buy ROVs and AUVs, because India has so much of population. Even risk is nothing. Risking your life is nothing here. So, whereas using a sophisticated AUV needs cost, first of all, investment of cost, then you need to train your manpower, you need cost and resources to maintain it. Okay. So then people are hesitant to buy, or even if they buy, there are cases where people don't utilize it because they fear that it's a 2 crore item. So I'm just giving an example. If I deploy it and lose it at sea, I'll have to answer to the management. So it's very funny. So that customer base is not built. So unless that building demand is there, we have to make a consistent and confident customer base. Here in India, I mean, the biggest customer base is, of course, Indian Navy. The Indian Navy is going all out to procure all these sensors. I mean, all these autonomous underwater vehicles, and they're building an AV squadron. Okay, so also, not squadrons in various parts of the country, which is very encouraging because you need trained manpower. You need to take the customer into confidence that they can actually exploit the AV, and this needs constant assistance interaction between the OEM and the user. So this is very important in developing that ecosystem in the country, and many startups in the country are into AV development. This is the right time, I think, we open up the customer base. So let us come to the concluding section. This is research opportunities. This is a very quick. So research in India, if you're talking about AV domain or domain of marine robotics, as people call it nowadays, you have research opportunities. You can do your masters in IIC Bangalore. That's a wonderful team which is working with Professor Suresh Sundaram, IICR Bhopal, Professor Sujit, IIT Bombay, Professor Leena Vachini's team, IIT Madras. We have a team working with Professor Suresh and Professor Akash. IIT Tirupati, IIT Palakkad, IIT Kharagpur also has a team working on dynamic AVs. NIT Silchar. These are some of the institutes. There are much more. Many private institutions. In fact, with BTech level, many people are working on AVs. But at a research level, if you want to work, these are the institutes. There are, of course, many I have missed here. And if you are looking overseas options are also fabulous. In fact, if you have the resources, I would recommend you please go overseas, get a taste of it, and come back. It's not that our facilities or our universities are lacking in anything. Our people are also exceptional. That means all these professors are also trained and they have done their degrees abroad. So you can get that first-hand feel and that heritage that they have. So University of Porto, Hui, Lisbon University, Memorial University, Southampton, Verona, and these are the places. And if you're looking at job opportunities in this particular domain, Cochin Shipyard is there just right next to you. They have a team called CSAS, Strategic and Advanced Systems team, who are working on very advanced and autonomous systems. Very small team, but very active and very nice team. All are youngsters. And we have some of our naval architects from the basic design also working closely with them for developing the autonomous systems. GRSC, similarly, Shipyard. They have a team working on autonomous systems. Basically, they're working along with startups. L&T has a strong team in the Aero Kochi, beautiful startup. Rekis Marine. So, again, this startup is started by a naval architect. So I'm all the more proud about this startup. They are doing wonderful job in autonomous surface vehicles and XLUVs. Sagar Defense is a company which is working on autonomous systems with our Navy. Salem Aerospace, wonderful team. They've worked with GRC for developing the autonomous underwater vehicle. Plancis Technologies, I4 Marine. So these are the places where you can get jobs. And government agencies, NSTL is there, NIO, CMERI, NIOT, Indian Navy. Indian Navy, as I said, submarine design group of Indian Navy is also developing. Also designing and actively involving in development of autonomous underwater vehicles with other agencies. So this is another place to be. I think, yeah, that's all from our side. This is a drone shot of our AV, which while we were doing trials at Kochi. That's all from my side. Thank you. I think I've taken a lot of time. Thank you for your patience, and the floor is open to you.
Sir, thank you for your insightful presentation, and this marks the end of the session. Now I request everyone to have a look at the chat box. Please fill up the feedback form provided there. We'll be having a Q&A session now. So all those who are interested in asking any questions may ask the questions that they have right now.
Sir, I'm Abdul Illas of batch 48. So my doubt is that you told us that all these trajectories, all these paths are programmed before launching these UAVs. So what happens when there's a sudden obstacle, like a sudden current or something that makes this UAV drift off its current path? So how will it find its initial path? Because you told us that there won't be much communication when it's underwater.
Yeah, Advait, it's a nice question. So you are following. Thanks. At least one person is there who has not slept through the lecture. I am proud of myself. So yeah, what is happening? See, this initial path will be fed by the supervisory planner or at the operator level. So that we call as mission planning. So mission planning is done using a set of waypoints. Now this is fed to the AUV. So this much you understood, right?
Yes, sir.
So now when the AUV is going into water, it is navigating by following the preset paths. Okay, it suddenly finds an obstacle. So let us say the front-looking sonar has identified that there is an obstacle in front, which was not in the mission plan. So this goes as a feedback to the mission computer. So there will be a supervisor sitting inside the onboard computer. I mean, inside the AUV. Inside the AUV, there is a mission computer system or an onboard computer, which actually does controls the complete mission. So this goes as a feedback first to the motion planner or the what you call. There is another card mostly which takes care of the guidance of the vehicle. So this obstacle information first goes to the guidance is nothing but see you are given a set of waypoints, isn't it? So this waypoint information is translated to the waypoints in which the vehicle understands. The vehicle may not understand lat long, so it may be understanding in some other terms like distance. So this guidance algorithm will realize that there is an obstacle at so and so coordinates. Now this information will be handed over to what will go as a command is basically the speed and turn rate at which you need to avoid the obstacle, or in some cases you have to dive down. You have to change the depth. But typically, it is if the obstacle is found in front, you always try to turn around. This command is given to the mission controller sitting inside the mission computer system. Now, the mission computer system executes this. It sees the command and it tries to execute this. So until the sonar stops seeing the obstacle, this is actuated. And once the sonar stops seeing the obstacle, now this command, the motion planner will stop generating the deviation command. Okay. So, and then what happens? The motion planner remembers the previous or the next waypoint that it is supposed to go, and it knows its present position because INS is there. So from there, it will try to reroute. It is called mission replanning or rerouting. So this rerouting happens, and it tries to go back to the or proceed to the next waypoint. So typically, if the AUV is moving and there is an obstacle coming in the front, this AUV turns around the obstacle and then again tries to navigate to the next waypoint. That is in simple line. I hope I have understood it. I mean, I have answered your question.
Yes, sir, yes, sir. As if like, like if it sees the obstacle, it will start turning, and it will only stop turning when it stops seeing this obstacle.
Correct. Yes.
Oh, okay, okay.
There are also some shy viewers who are shy to speak. They have put their doubts in the comment box. Can you please?
Okay. Okay, what are the MI algorithms? You mean machine learning algorithms considered for object detection and object recognition? There are some deep learning techniques which are employed, but there is a team who is working on this even at NSTL and also our sister laboratory at CARE. I think some open source software is there. YOLO is one. I don't remember the exact framework which they are working on. I'll get back to you. But if you just search in the internet, you will get enormous literature on this. Sonar image processing. I am not directly working on this area, so I don't remember the software architecture that they are working. Is there any openings in DRDO underwater? Yeah, of course. We have openings. In fact, 2 months back, we were looking for somebody who could work on our simulations. But unfortunately, see, what happens is that we are a government agency. We cannot immediately recruit like any private agency will do. So we have to move the case through headquarters, and it will be good 1 year once the recruitment happens. There are procedures involved with the government. They have to take sanction from the government and all this. So what we did was to hire 2 people on contract basis. 2-year contract, maybe we hired a couple of people. So periodically, when the opening comes up, we'll let you know. But then we were looking for somebody who had hands-on experience in Gazebo, or we didn't get anybody in Gazebo. So we got 2 guys who were good in Python. So we are now training them in Gazebo. Are the concept of digital twin and hills same? No, they're not same. They are related. Okay. Hills, yeah. Anileka Tambi. Good questions you're asking. So, may I know, are you a student?
Sir, I am a research fellow.
Oh, good. At Cochin University.
Yeah, at Cochin University.
What is the area of your work?
Maritime surveillance and verification of AI/ML system.
Oh, wonderful. Good. So, hardware in loop simulation and digital twin is not exactly the same. Digital twin is basically mostly a software-based solution, whereas Hills may hardware is involved. So that is my understanding. Your actual hardwares are put in a lab environment without the vehicle is not in, the actual vehicle is not there, but you have your subsystems in simulated environments, and then you try to recreate the actual mission, and you see the effectiveness of these subsystems and whether the softwares are able to communicate. The ICDs, everything is checked. Whether there are any errors in communication. That is case. Digital twin is more like you are trying to replicate the complete AUV system in a software architecture. So that is little more software intensive. See, I think what I understood, my limited understanding is that what Gazebo or these Dune architecture integration, this kind of simulators are in fact a sort of digital twin. It may not be an exact replica of exactly what theoretically is meant by digital twin, but they are almost there.
Okay. Thank you, sir.
Yeah, thank you. I thought you were asking me to leave. Somebody typed.
No. Actually, the way you have explained that hardware in loop, it seems to be similar with digital twin. That's why I asked whether the concepts are
Fine,
same.
fine.
or not.
Your question is fine. I was just joking about the comment. Then I thought,
Okay, fine.
please
Okay.
leave your valuable feedbacks. I thought it was please leave. Fine. Okay.
Shiji, this is Manoj. I have a question. Like in the very early part of your presentation, you were showing some mission planning software with the electronic chart. Are those electronic charts available? I mean, is it really
Yes, sir.
accessible?
Yeah. In fact, this S63 charts, they're called ENCs, electronic navigation charts. So S57 and S63 charts are available in the open domain for purchase. You can, what I understand is that you can readily procure it from, like you buy from Amazon. No, you can through online. You can easily procure.
And is it for a specific region or so?
Yes, it is region based.
Oh.
So based on your area of this thing, you can buy them. And each area, I think the rates may be different, and resolution also depends on the area.
And is that available for inland?
Inland, I am not sure, sir, because inland I have to see, because this mostly it is for the oceans.
Okay.
Inland, I'm not sure. But then I have seen people using Google Earth in a customized way for mission planning. They're all open source softwares which are used for customizing this softwares. But of course, inland may you will not have the depth information. That is the issue. Lat long you will get. Depth maybe you may have to either generate some route survey depth, or you have to get it from the any available hydrographic survey or something.
Okay.
So,
yeah, thank you.
Sir, I'm Ritul from the. Hello, sir. Hello, sir. Sir, I'm Adil from the 48th batch of technology.
yeah, Adil, tell me.
Yeah, so I just wanted to ask, like you mentioned, most of the AUVs are like slow-moving AUVs, right? And I wanted to know, like, if are there any chances when you have to use like fast-moving AUVs, like any specific situations?
Yeah, in fact, Russia has developed. In fact, they are not fast; they are super fast. Okay, so typically, see what happens is that as I told in the beginning, AVs are mainly role centric. Okay, so when you have to do a surveillance, you have to use a particular sensor. So that will be a sonar. This sonars will require a range of speeds for optimal operation. If you exceed that speed, if you are exceeding that speed, what happens? Sonar performance will deteriorate like anything. You will not get any meaningful results. That is why most of the AVs are slow moving vehicles. Now, when you need speed, speed is used by AVs only when they attack, and they are very rare. I can say only one system which I know, which is a nuclear powered AEV, and there are debates whether it can be called as an AEV or a underwater missile or underwater torpedo systems, because they claim it to be a nuclear powered AEV, and they are claiming exorbitant speeds. I don't even remember. I think it is very high. Even compared to conventional torpedoes, their speeds are claimed very high when they want to surprise the enemy with a high speed attack. But otherwise, this is where. So tomorrow, when you are actually making AEVs which can carry weapons, you may need a quicker delivery. You may need to carry the weapons and sprint to a location and fire at the enemy. Or another possibility is that you are actually doing covert surveillance at a particular location, and then enemy spots you or detects you, and there is a high chance that they will pick you up, because you are a dumb autonomous underwater vehicle. You cannot see that enemy is coming, but the moment you sense that somebody is near or some obstacle has come near, because any other boat or ship will be seen as an obstacle, it is coming too close, then you sprint away from the location. So this is one possible area where AUVs can be requiring high speed. Okay.
Okay, sir. Okay.
Hi, sir. My name is Rahul. I'm doctoral student of Manoj, sir.
Okay. Okay. Rahul. Hi, Rahul.
Sir, not Iro, Rahul.
Yeah, I said hi, Rahul.
Okay. Hi, sir. So first of all, it was nice presentation, and thanks for including ISC Explorer in your presentation, because I work on the Explorer AUV, and right now I'm at Memorial University also.
Oh,
So it was
wonderful. That's
nice.
wonderful.
I have a couple of questions. So first is regarding docking. So this ISC is now developing docking facility for AUV. So how is the trend in India?
I lost you. What were you saying? ISC?
ISC is now developing docking system for the AUV, autonomous docking.
Yes.
So what is the current trend in India for docking systems?
Yeah,
That's
good
the first
question. Good question. In fact, docking systems are essential because, as we discussed sometime, the recovery is a very tedious task, and again you have to redeploy the AV, so that's a tedious task. Then docking stations are being developed by globally multiple AV developers, so that you somehow you lower the docking station either from a mothership or it is a permanent fixture in the geography. Underwater, AEV just enters itself into the docking station. It transfers the data through some connector, and also it gets recharged, and it is, instead of getting picked up, it depending on the command, it can redeploy itself. So this is the concept of docking station. And just speaking for the knowledge of all, so this docking station is a upcoming concept. So in India, I know that at the academic level, people are working. Okay, so at academic level, there have been very good publications in people are working. But at implementation level, I have seen our user, Indian Navy, floating out expressions of interest for the industry to come up with docking station, and I believe people are already working on it. But I don't know about, or I don't remember first-hand information on who is working. There may be people working. I'll find out about it.
Okay, sir.
Yes.
So then, second question I have.
People are working. Yeah, definitely people are working, and it will be. I'm sure it will be taken up by somebody.
Okay.
In fact,
second
our
question
NSTF's Swarm team also, they're considering this docking station. In fact, they're not trying to develop it on their own, but they're trying to get an industry to develop. So that is there.
Okay, sir. So second question is like, there is IMO guidelines for the ship standard trials, but for AUVs and all underwater vehicles, we don't have it.
Correct.
So each time during when you do a trial, how do you know that you are having a best performance, or how do you make that decision, final decision?
Yeah, that's a challenge. That's a big challenge, because when we do the trials, so far we have done trials in restricted waters. So we have not gone to open sea, which is a challenging environment. But I mean, with the current vehicle platform, generally, see what happens is that this users are asking us to develop AV systems which are compliant with the Cold-Rex pollution regulations by IMO. See, we don't have regulations. So when we look at the existing regulations, it will be very difficult to implement it for the AV. So we are keeping our fingers crossed. So what best we can have is obstacle avoidance algorithms. Okay. So again, it all depends on what kind of sensor you are using for detecting obstacle, what kind of algorithm you have, what is the capability of your platform to avoid obstacle. So here, in open ocean, as you know, the probability of finding anybody else is very, very limited. This all become relevant when you come to congested waters like harbor or your port transit, wherein other vessels will be there, congested traffic will be there. So it is, there are many things. One is that very unlikely that an AAV will be operated there, but nevertheless, let us consider that AAV is transiting back to harbor. It is an AAV which comes to harbor and goes back. In that case, right now what we have is a capability for the operator to actually see the AAV in such an environment in real time, and then remotely steer the AAV to avoid it. See, suppose the onboard obstacle avoidance algorithm, it is unable to avoid, and it is seeing multiple obstacles, let us say. Okay, so it is unable to take a decision. It reports to base that I am unable to take a decision. Please bail me out. In that case, the operator can intervene and remotely steer the AUV. That is one option to maintain safety. Other option is the other important point to note here is that on surface, when the vehicle is moving, it is very unlikely that your platform, AUV is a very slow moving platform. So it will create substantial damage, or even the manned platform can actually steer away, seeing that an AUV is coming near its obstacle avoidance algorithm as failed. Where it happens is that when the vehicle is trying to surface, it is likely that it may hit some ship which is already there, or a boat, fishing boat or something which is already there. That is a likely possibility. So here we are again working on implementing the obstacle avoidance algorithm. That is what we are doing. The cold regs are not talking about this aspect of the autonomous underwater vehicles, which I think IMO will soon come out with something. But I think ultimately the solution is to have a acoustic sensor, or even have an underwater camera. But camera again, range is less. And the moment you see something, when you're trying to surface, you'll be at a small pitch angle at least. So your field of view will be tilted slightly upward. So it is not that very close to the water surface where the sonar won't perform, but at least 50 meters below the water surface, you're able to see that something is there and you don't surface. So that is one option. So this is the most important part of obstacle avoidance as far as AUVs are concerned. Did I answer your question?
Yeah, that was a good answer. I have two more questions. May I ask that because you had a wonderful presentation. That's why I have a couple of two more questions related to naval architecture. So maybe this high endurance AUV, HAUV of NSTL, maybe the self-propulsion test might have been done in the labs there itself. So maybe the self-propulsion point might be also estimated. I have once visited this HAUV lab at NSTL, and I have seen in the board there the various weight balance log files. I mean the weight balance sheet of the AUV is also written there, weight file. So in practical, when you go to the sea, how much variations do you expect when compared to that of what you did in the experiment?
Okay. But it means weight and self-propulsion. Okay.
Yeah, because initially when we do self-propulsion, we don't have the exact idea about the weight.
Fine. You may be correlating with the surface ship picture. Fine. Okay. I get your point. See, in underwater vehicles, it is weight and buoyancy. In surface ships, if you that analogy, it is not completely correct. Okay, first I'll answer your last part of the question. Density variations will be affecting the AV, because there are two aspects in which I will answer that. One is the density variation can be if it is an open sea. Okay, the density variations are more or less seasonal. It is not that in a single day or 2 day there will be a drastic change in density, unless it is a river mouth or close to harbor. In harbor, the situation is very dynamic because, or a river mouth, the situation is very dynamic where mixing of waters take place. So there we have actually measured the waters in Kochi because of this pier. So some days we could find that the density is 1016 kg per meter cube. Okay. And some other days we have even measured 1028 kg per meter cube. So this for my vehicle, this gives a density variation of around 50 to 60 kg. And that is almost similar to my positive buoyancy margin. So this we take care meticulously. That's why I said weight management is extremely important for AUVs, because the margin of positive buoyancy that you have because of the density variation, you should be very careful that it is not going to it is not going finally end up in losing the vehicle, because vehicle will sink. Now, coming to the first part, weight is not directly related to the self-propulsion point of the AV, because here, unlike the surface ship, I understand that the displacement changes and you are thinking that the resistance is increasing. But here, you must remember that always the AV will work completely underwater. So whether it is 6 tons or 6.1 tons or 6.2 tons, the drag is always same once it is underwater. But the loading on the fins will increase. if it is a positively buoyant and say the weight has increased and it has become less positively buoyant, then the loading effort on the fins for sustaining it at that depth, that will change, not the powering part. I
Okay,
hope
sir.
I have
Yeah, that answered the question, sir. One last question, sir. I see that HAUV is being given with X configuration at the stern side, compared to the conventional plus configuration or cruciform configuration, which we usually use, which is easy to maneuver also. So, how challenging was it for you while using the X configuration to study its dynamics, control everything?
you are asking about the difficulty experience.
Yeah, exactly.
We went through a lot of difficulties. In fact, we want to do more trials in order to answer that question. Honestly speaking, we have insufficient data to answer your question. But in the implementation stage itself, we went through a lot of difficulties. And at least on the bench level and the initial trials, it is behaving okay. But once you do more dynamic trials at depth, only we'll be able, and depth maneuvers, I mean, we'll be able to do. Horizontal maneuvers doesn't matter much as I understand, but depth maneuvers and the resolving part, the roll stabilization, all these things matter. It is always easier and straightforward to go for a plus pump configuration. In fact, I would have chosen a plus pump configuration, but the decision came from our hydrodynamics group. So they have seen it from the perspective of the positive buoyancy it is carrying. The vehicle is positively buoyant. So to balance that, XFOM, when you have XFOM, all the four rudders will be contributing at the same time. So that was one of the reasons which why they proposed the XFOM, accepting the challenge, and the controls people, as you rightly pointed out, struggled with the implementation, resolving the angles. Yeah, that's right.
Okay, sir. So then, was there any particular reason like why you awarded a bow control plane? Because Explorer is having a bow control plane, and this is a 10-meter long AUV, and you don't have a bow control plane. So, and also it's a slow speed AUV. So,
that's true.
was
But
there any particular?
no, see, Bluefin is kept only if it is essential. Otherwise, again, it becomes a liability. So when we did our simulations, we found that the vehicle is stable. We didn't have any low speed stability issues. But again, as I said, we have to do more depth maneuvers at the speeds which we were moving, and it all depends on your relative position of your center of gravity and center of buoyancy. Okay, so we didn't have much issues there. So that's why our design and simulations did not give us the requirement of a Bluefin. So we did not keep it. Simple as that.
Okay.
Yeah.
Okay, sir. Thank you, sir. Thank you for answering all the questions.
Good questions. Yeah.
Thank you.
Yeah. Somebody has asked, yeah, I think that question is can software reliability be? Yeah, definitely. Can software reliability be a challenge to AUVs? 100%. So, in fact, that is one of the most important aspects of it. So, we have an IVNB team, internal verification and validation, and that's why I said, see, there are established architectures like Dune and Neptus, which from LSTS or Moose. These are time tested. So the basic architecture is established. So you need not reinvent the wheel. So you can straight away start using, because they are open source and they can customize it. That is what most of the people are doing. And at some point they customize it to with their branding. Whereas being a military organization, we are partly we are using our own softwares, but we take care of the reliability. The reliability is a very crucial aspect. Yeah.
I guess this marks the end of the Q&A session. For further queries, you may contact Mr. Shiju directly. Now, before concluding, we would like to present a certificate of gratitude to Shiju John for honoring this event and delivering a wonderful talk.
Oh, that's wonderful. Very nice, very nice. I would like to thank Satish Babu sir. I saw his name in the just now. I saw his name. So we have not met for a long time, sir. But thank you so much for if you are there.
I
Sir,
hope
thank you, sir.
everyone.
In the absence of our SNAS secretary, I speak for him. This is our fourth series of webinar, and this is the most intense and most information blasting seminar we have had. Thank you, sir, for your effort. You have set aside your time despite your busy schedule for us. Thank you so much for your wonderful work, sir. Thank you.
Thank you so much. No, I love interacting with students. I unfortunately, when you guys came here, I was unable to meet you because I had to move around with some other work. Thank you so much. Because I hope I have educated some and inspired some people. All the best for all of you.
Sir, your presentation was going live on YouTube, and we have been receiving so many messages saying that your work is wonderful. Once again, thanks a lot, sir, and appreciate it.
Oh, thank you, thank you. I would request you to please share that link with me. Just,
Sure, sir, sure.
thank you, thank you. I forgot to say thanks to Professor Anu. In fact, he was when he came here, we had a discussion. So he was the one who urged me to give this webinar. I would extend my gratitude to. I could not see his name yet. Some other name is there.
Sir, some people in the comment box are asking for your contact number.
Yeah, my number is with Navneet. I don't want to flash it in the this thing. You can take it from Navneet if it is all right.
Okay, okay.
And you can share it with whoever is asking.
Okay, fine.
Okay. Thank you.